Welcome to Sleepy Science Student, where we explore the deepest mysteries of the universe, one gentle whisper at a time. Tonight, we're embarking on a slow, soothing journey into one of physics' most profound and elegant frontiers, the Planck scale, where space and time themselves begin to reveal their most intimate secrets. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating about the very fabric of reality itself. Not the worst way to spend a sleepless night, really. Before we venture into this strange and beautiful realm, where the rules of physics transform into something altogether different, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this quiet little channel grow and means that more curious minds like yours can find their way here to explore the cosmos together. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Stockholm at midnight, or listening from a comfortable chair in Melbourne at dawn while the world still sleeps around you? Perhaps you're watching from somewhere in between, in a time zone where the afternoon light is still gently fading. Let me know in the comments. It's always such a joy to see the curious community scattered so gently across the globe, all wondering about the same profound questions. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert or worry about understanding every detail. Just let the words wash over you like soft moonlight filtering through a window. Let your shoulders relax. Take a slow, gentle breath. And as we begin this peaceful voyage into the realm of Planck physics and quantum gravity, remember that this video is for educational and relaxation purposes only. It's not intended as a substitute for professional scientific study or medical advice, though it might make your mind feel pleasantly peaceful and your thoughts drift gently towards sleep. Ready? Let's begin. Let's start with a question that has quietly haunted physicists for centuries. Is there a smallest possible size? A tiniest moment? A final, irreducible pixel of reality, so minute that nothing smaller could possibly exist? Most of us live in a world of comfortable middle scales. We see tables and chairs, mountains and oceans, stars and galaxies. Our intuition is built for objects we can hold in our hands and distances we can walk across. But the deeper we peer into reality, down through layers of structure that seem to go on forever, we eventually reach a point where our intuition begins to falter. We reach the realm where physics itself transforms into something strange and beautiful and profoundly different from everything we experience in everyday life. You might think that space is infinitely divisible. After all, if you have a distance of 1 meter, you could theoretically split it in half to get half a meter, and then you could split that in half again, and again, and again. Following this logic, you might imagine that you could keep dividing forever, approaching smaller and smaller distances without ever reaching a true minimum. But actually, modern physics suggests something quite different. Deep within the structure of reality, hidden far below even the scale of atoms and subatomic particles, there appears to be a fundamental limit to how small things can get. Let's pause for a moment and imagine something. Picture a ruler, an ordinary ruler perhaps, marked with centimeters and millimeters. Now imagine zooming in on one of those millimeters. You could see individual micrometers. Zoom in further, and you'd find nanometers, the scale at which atoms begin to appear. Continue zooming, and the atomic realm would open before you like a hidden city. But what happens if we keep going? What if we zoom in 10 more times, 100 more times, 1,000,000 more times? This journey inward is not a gentle descent into an infinite regress. It's a voyage toward a frontier, a boundary beyond which our current understanding of physics begins to fragment and reform into something altogether new. At this frontier lies the Planck scale, named after the physicist Max Planck, whose quiet genius in 1900 laid the foundation for an entirely new understanding of the universe. The Planck scale is not just the smallest distance in space, it's not just the shortest interval of time, it's something far more profound. It's the scale at which gravity, that most fundamental force that shapes the universe, begins to dance with quantum mechanics, the strange and beautiful logic that governs the realm of the very small. Let me paint you a picture of what makes this scale so special. For most of the 20th century, physicists lived with a peculiar divorce. On one side, there was Einstein's theory of general relativity, a description of gravity so elegant, so mathematically beautiful, that it describes the entire universe from the perspective of curved spacetime. Gravity, in Einstein's vision, is not a force pulling on objects. Rather, it's the geometry of space and time itself, warped and curved by the presence of matter and energy. It's a bit like how a heavy ball placed on a rubber sheet creates a depression, causing other balls to roll toward it. But this analogy only hints at the true complexity. In the real universe, both space and time themselves are part of the fabric that bends and curves. On the other side, there was quantum mechanics, a description of the microscopic world so successful, so experimentally verified, that it explains nearly everything about atoms, electrons, light, and the behavior of matter at small scales. In the quantum realm, particles exist in states of superposition, existing in multiple places at once until observed. Energy comes in discrete packets called quanta. Particles behave like waves. The act of measurement fundamentally changes reality. Everything is probabilistic, uncertain, alive with possibility. For decades, these two pillars of modern physics coexisted peacefully, each supreme in its own domain. General relativity ruled the cosmos, the vast, the immense, the gravitational. Quantum mechanics ruled the microscopic, the tiny, the atomic, the subatomic. But what happens when these two realms collide? What happens when you try to apply quantum mechanics to gravity itself? What happens at scales where both effects are equally important? That's where the Planck scale enters. It's the scale at which quantum gravity becomes the dominant force. It's the scale where our current understanding of physics breaks down, and something deeper, something we don't yet fully understand, emerges. And it's a scale so unimaginably small, so profoundly removed from our everyday experience, that it's almost impossible to truly grasp just how small it really is. Take a breath. Let's talk about scale for a moment. The distances we're about to explore are so incredibly minute that our minds struggle to hold them. Consider this. If you took an atom, say, an atom of hydrogen, one of the smallest atoms, and magnified it to the size of a sports stadium, then an electron orbiting that nucleus would be like a tiny marble somewhere near the edge of that stadium. But the nucleus itself, at that magnification, would only be about the size of a grain of sand in the very center. Now, if you took that grain of sand and magnified it again to the size of a sports stadium, you'd find protons and neutrons. And if you magnified one of those to the size of a sports stadium, you'd begin to find the quarks inside. And still we haven't reached the Planck scale. We'd need to continue this journey billions upon billions of times further. The Planck length, as it turns out, is approximately 10 to the negative 35 meters. To give this some context, your smallest fingernail is perhaps 1 millimeter. That's 10 to the negative 3 meters. The ratio between the Planck length and your fingernail is roughly the same as the ratio between your fingernail and the observable universe itself. Think about that for a moment. The Planck length is as small compared to a millimeter as a millimeter is compared to the vast cosmos stretching across billions of light years. It's a scale so unimaginably tiny that even writing out the number feels almost insufficient to convey just how small it truly is. And then there's the Planck time. Just as there appears to be a smallest possible distance, physicists have calculated that there may also be a smallest possible interval of time. The Planck time is approximately 10 to the negative 44 seconds. This is the time it would take light, the fastest thing in the universe, to travel across a Planck length. At scales shorter than this, our theories predict that time itself might cease to behave as we normally experience it. Time might become quantized, broken into discrete units, or time might lose meaning altogether, or something entirely different might happen. something we haven't yet dreamed of. You might think that these scales are merely theoretical curiosities, abstract numbers that physicists calculate, but which have no bearing on the real world. But actually, the Planck scale has profound implications for how we understand reality itself. It hints at a revolutionary possibility, that space and time, which seem so continuous and smooth to us, might actually be fundamentally grainy at the tiniest scales. They might be woven from discrete units, like the pixels on a screen. If you zoomed in far enough on reality, you might find that space is not infinitely divisible after all. You might find a fundamental quantum of space-time itself. This is not just a mathematical game. This touches on the deepest questions of existence. Is the universe fundamentally continuous or discrete? Are space and time fundamental, or are they emergent phenomena, arising from something even more basic? What lies beneath space-time itself? These questions have occupied some of the finest minds in physics for the past century, and they remain tantalizingly, beautifully unresolved. So as we continue this journey together, we're not merely exploring an obscure corner of theoretical physics. We're peering into the very foundations of reality. We're asking what the universe is made of, how it works, and what secrets it still holds close to its heart. We're engaging in the most fundamental form of curiosity, the desire to know what lies beyond the known, to gently push against the boundaries of our understanding, to see if there's something waiting for us just beyond the edge of what we can perceive. Now we move gently into the heart of the mystery, understanding how gravity and quantum mechanics came to be at odds with each other, and why this conflict has led physicists to the doorstep of the Planck scale. Let's travel back in time for a moment. Picture yourself in the late 19th century, when the world of physics seemed almost settled. Newton's laws of motion and gravitation had ruled for 200 years, explaining everything from falling apples to orbiting planets with remarkable precision. The universe, it seemed, operated like an enormous, elegant machine. Cause and effect were clear. Reality was deterministic. If you knew the position and velocity of every particle in the universe at one moment, you could theoretically calculate the entire future. The world felt orderly, knowable, safe. Then came Einstein. In 1905, with his special theory of relativity, he showed that time is not absolute. It's not universal. Time moves differently depending on your speed. The faster you travel, the slower time ticks for you relative to someone standing still. This wasn't just a theoretical curiosity. Scientists could measure it. Atomic clocks on fast-moving airplanes actually ticked more slowly than identical clocks on the ground. Reality, it turned out, was far stranger than Newton had imagined. But Einstein wasn't finished. In 1915, he published his theory of general relativity, and the world of physics transformed completely. Gravity, he proposed, wasn't a force at all in the Newtonian sense. It wasn't some invisible hand pulling objects toward each other across empty space. Instead, gravity was the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space and time around them, and other objects moving through this curved space-time experience what we call gravity. It's a bit like how a marble rolling on a flat table moves in a straight line. But if you place a heavy ball on the table, the marble will curve its path and roll toward the ball, not because the ball is pulling it, but because the table itself is now curved. This theory was extraordinary. It explained not just gravity, but also light. Light, Einstein showed, travels through space along the straightest possible path. But if space itself is curved by gravity, then light bends around massive objects. Predictions made by general relativity seemed impossible, utterly divorced from common sense. And yet, when astronomers looked at the sky during a solar eclipse in 1919, they observed starlight bending around the sun exactly as Einstein's equations predicted. The universe was confirming this wild, beautiful theory. For decades, general relativity stood as one of humanity's greatest achievements. It explained the cosmos on the largest scales. It described black holes, objects so dense that even light cannot escape their gravity. It explained the expansion of the universe itself. It was and remains one of the most successful theories in the history of science. But in the early 20th century, something else was happening on the other side of physics. In the realm of the very small, scientists were discovering that atoms weren't indivisible after all. They had structure. They contained electrons orbiting nuclei. And when physicists began to study these tiny realms carefully, they found that the old Newtonian laws simply didn't apply. Atoms didn't behave like miniature solar systems. Electrons didn't orbit like planets. Instead, electrons seemed to exist in clouds of probability. They could be in multiple places at once, and when you tried to observe them, to pin down their exact location, something strange happened. Your act of observation changed the system itself. Max Planck discovered something remarkable in 1900. When he studied the radiation emitted by hot objects, he found that energy wasn't emitted smoothly and continuously, as classical physics predicted. Instead, energy came in discrete packets, which he called quanta. Light, it seemed, came in bundles. A light wave wasn't truly a continuous wave at all, at least not when you looked closely enough. It was made of particles called photons, each carrying a specific amount of energy determined by the light's frequency. The higher the frequency, the more energy each photon carries. This was the birth of quantum mechanics. Over the following decades, physicists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed a comprehensive theory of the quantum realm. They found that at the scale of atoms and subatomic particles, nature followed probabilistic laws. Particles existed in superposition, in multiple states simultaneously, until measured. The position and momentum of a particle couldn't both be known with perfect precision simultaneously. There was a fundamental uncertainty built into reality itself. Energy, momentum, and angular momentum all came in discrete quanta. The universe at small scales was fundamentally different from the universe at large scales. Take a breath. Let's pause and think about what this meant. For centuries, physics had been built on a foundation of determinism and continuity. The universe was a clockwork, ticking away according to fixed laws. But quantum mechanics suggested something radically different. Reality was probabilistic. It was grainy. It was fundamentally uncertain. Not because we lacked information, but because nature itself was uncertain at the deepest level. And here's where the conflict emerged. General relativity and quantum mechanics are beautiful theories, but they speak different languages. General relativity is a theory of smooth, continuous spacetime. It's classical, deterministic, not probabilistic. Quantum mechanics, on the other hand, is fundamentally probabilistic. It's about discrete quanta, not continuous fields. It's about probability waves and superposition, not definite positions and velocities. For most practical purposes, this didn't matter. General relativity governed gravity on cosmic scales, and quantum mechanics governed particles on atomic scales. These domains didn't overlap. You never needed to apply quantum mechanics to gravity in everyday situations. But theoretically, the incompatibility bothered physicists. If both theories were correct, and mountains of experimental evidence suggested they were, then there should be a way to reconcile them. There should be a unified framework that encompassed both the very large and the very small. The problem became acute when physicists tried to imagine what happened in the early universe. In the Big Bang, all the matter and energy of the cosmos was squeezed into an infinitesimal point. Under such extreme conditions, both gravity and quantum effects would be equally important. You couldn't ignore either one. You'd need a theory of quantum gravity. But combining quantum mechanics and general relativity turned out to be incredibly difficult. When physicists tried to do the calculations, they got infinities. The math didn't work. Something was fundamentally broken in their approach. This is where the Planck scale enters the story with quiet elegance. When physicists estimated the scale, at which quantum gravity effects would become important, the scale where gravity's effects would be as significant as quantum mechanical effects, they arrived at a specific set of numbers. These numbers defined what we now call the Planck scale. At scales larger than the Planck scale, you could usually ignore quantum effects in gravity. At scales smaller than the Planck scale, quantum effects would dominate. And right at the Planck scale itself, both effects were equally important, and neither theory provided reliable predictions. You might think that the Planck scale is merely an artifact of our current mathematical formalism, that if we had a better theory, we wouldn't need to invoke this special scale. But actually, the Planck scale has a kind of universal significance. It's not just about combining two particular theories. It's about fundamental limits in nature. Consider what happens at the Planck scale. The energy density becomes so enormous that, according to general relativity, it would create a black hole. But a black hole this small, only about the size of the Planck length, would have such enormous tidal forces that quantum mechanics predicts it would immediately evaporate in a flash of radiation. So even a black hole at the Planck scale exists in a kind of limbo, neither fully governed by general relativity nor by quantum mechanics. This suggests something profound. The Planck scale might not just be where our current theories break down. It might be where nature itself has a fundamental grain. It might be where spacetime transitions from being a smooth, continuous fabric to something fundamentally discrete. It might be the scale of quantum foam, a seething, bubbling sea of virtual particles and quantum fluctuations where spacetime itself flickers into and out of existence billions of times per second. Not just is the Planck scale a theoretical boundary, it's also a physical one. At the Planck scale, the gravitational force becomes as strong as the other fundamental forces, the electromagnetic force, the weak nuclear force, and the strong nuclear force. For most of the universe and most of the time, gravity is by far the weakest force. An electromagnet can lift a small piece of iron against the gravitational pull of the entire Earth. But at the Planck scale, gravity reasserts itself. It becomes as powerful as the other forces, and perhaps it merges with them into a single, unified interaction. This brings us to one of the deepest dreams of theoretical physics, the grand unified theory, or GUT, and beyond it, the theory of everything. Physicists have long wondered if all the forces of nature, gravity, electromagnetism, and the nuclear forces might be manifestations of a single, underlying interaction. At the extremely high energies present at the Planck scale, these forces would all have the same strength and might merge into one unified force. This is not mere speculation. The electromagnetic force and the weak nuclear force have already been unified in what's called the electroweak force. And there are compelling theoretical reasons to believe that this could be further unified with the strong nuclear force at very high energies. Gravity is the holdout. Bringing gravity into the fold has proven extraordinarily difficult, but many physicists believe it's possible in principle. Imagine, if you will, standing at the moment of the Big Bang itself. The entire universe is compressed into an infinitesimal point of unimaginable density and temperature. All four fundamental forces are merged into one superforce. Space and time as we know them haven't even emerged yet. The laws of physics as we understand them cease to apply. This is the realm of quantum gravity, and this is the realm of the Planck scale. Understanding what happened at this moment, how the universe began, what preceded it, whether time itself had a beginning, requires a theory of quantum gravity that we still don't fully possess. Here's something to gently ponder. We live in an era where we've barely begun to peek beneath the surface of reality at the Planck scale. We have no direct experimental access to this realm. The energies required to probe these scales directly are billions of times higher than anything we can create in our laboratories. The Large Hadron Collider, humanity's most powerful particle accelerator, can explore scales down to about 10 to the negative 19 meters. But the Planck scale is 10 to the negative 35 meters. We're off by a factor of a billion. To directly explore the Planck scale would require an accelerator larger than the entire solar system and more energy than humanity could conceivably harness. And yet, despite this seemingly insurmountable barrier, physicists have found ways to probe the Planck scale indirectly. They study black holes and how they evaporate. They examine the structure of spacetime through quantum fluctuations. They look for signatures of Planck scale physics in the cosmic microwave background, the ancient light that was released when the universe was only 380,000 years old. They develop mathematical theories like string theory and loop quantum gravity, which attempt to reconcile gravity and quantum mechanics in ways that might become testable someday. The conflict between general relativity and quantum mechanics remains one of the great unsolved problems in physics. But as we've seen, it's not a flaw in one theory or the other. It's a hint of something deeper. It's nature's way of telling us that at the Planck scale, reality transforms. Space and time, which seem so fundamental to us, might emerge from something more basic. The universe might be woven from something we haven't yet discovered. And the Planck scale, so impossibly small, so profoundly removed from our everyday experience, might be the key to understanding everything. Now let's drift gently into the numbers themselves. Let's explore what the Planck length actually is, how physicists calculated it, and what it reveals about the fundamental nature of reality. The Planck length emerges from a beautiful mathematical insight. In 1899, just 1 year before he discovered the quantum nature of energy, Max Planck realized something elegant. There exist 3 fundamental constants of nature that, when combined in just the right way, produce a length scale. These 3 constants are like the ingredients in a recipe for the universe itself. The first ingredient is the speed of light, usually written as c. Light travels at approximately 300,000 kilometers per second through the vacuum of space. Nothing can travel faster than light. It's a cosmic speed limit, woven into the very fabric of spacetime. This constant appeared in Einstein's theory of relativity, fundamentally connecting space and time. The second ingredient is the gravitational constant, written as g. This constant determines the strength of gravity. It tells us how strongly 2 objects attract each other due to their mass. A more massive object has a stronger gravitational pull, but the strength also depends on the distance between objects and on this fundamental constant g. The gravitational constant is remarkably small, which is why gravity feels so weak in our everyday lives compared to other forces. You can lift a pencil against the gravitational pull of the entire Earth using just your fingers. Only when objects become truly enormous, like planets or stars, does gravity's strength become undeniable. The third ingredient is Planck's constant, often written as h, or in its reduced form as the h-bar symbol. This constant appeared in Planck's own work on the quantum nature of light and energy. It sets the scale for quantum effects. When energies or actions are large compared to Planck's constant, quantum effects are negligible, and classical physics applies. When energies or actions are small compared to Planck's constant, quantum effects dominate, and the universe behaves in strange, counterintuitive ways. Now, here's where the elegance emerges. If you take these 3 constants, the speed of light, the gravitational constant, and Planck's constant, and combine them in a specific mathematical way, you get a length, just a length, nothing else. You get the Planck length. It's as if nature itself is telling us, here is a fundamental scale. At this distance, the universe transitions from one regime to another. The calculation goes like this. You take Planck's constant and divide it by 2 pi. You multiply by the speed of light. You divide by the gravitational constant. You take the square root of the whole thing. And out comes the Planck length, approximately 1.616 times 10 to the negative 35 meters. Let's pause for a moment and appreciate what this means. This number wasn't discovered by direct measurement. There's no instrument that could ever measure something this small. Instead, it emerged from pure mathematics, from thinking carefully about the fundamental constants of nature and combining them in ways that reveal hidden structure. It's a bit like how a mathematician might discover that a certain geometric pattern exists without ever actually building it physically. The Planck length is a signature hidden in the constants of nature, waiting to be decoded. But what does this length actually represent? Why is it special? Here's one way to think about it. According to quantum mechanics, you can't measure a distance with perfect precision. There's always some uncertainty. The more precisely you try to measure a distance, the more energy you need to concentrate into your measurement. But here's where gravity enters. As you concentrate more and more energy into a smaller and smaller region, the gravitational effects of that energy become stronger and stronger. At some point, you reach a regime where the energy you're using to make your measurement becomes so concentrated that it creates a black hole. At that point, you've concentrated so much energy into such a small region that gravity completely overwhelms the situation. You can no longer extract information from that region. The very act of trying to measure a distance at that scale would destroy the ability to measure it. That critical scale, where the uncertainty in quantum mechanics meets the overwhelming power of gravitational collapse, is the Planck length. At scales larger than the Planck length, quantum mechanics and general relativity peacefully coexist. You can make precise measurements without worrying about creating microscopic black holes. But at scales smaller than the Planck length, both effects are equally important. You can't ignore either one, and our current theories simply can't handle this regime. You might think that the Planck length is merely an abstract number, devoid of physical significance. But actually, it represents a fundamental limit on how much information can be extracted from a region of space. This connects to deep insights about black holes discovered by Stephen Hawking and Jacob Bekenstein. They showed that a black hole's entropy, roughly speaking, the amount of information it contains, is not proportional to its volume, but rather to its surface area. This is bizarre. Normally, a three-dimensional object's information content grows with its volume, but for black holes, it grows only with surface area. This suggests that space itself might be holographic in some sense, that the three-dimensional world we perceive might be a projection of information encoded on a two-dimensional surface. The Planck length connects intimately to these ideas about black holes and information. A black hole the size of the Planck length would be the smallest possible black hole. It would contain about 1 unit of information, the minimum amount of information that spacetime can carry. Such a black hole would be extraordinarily unstable, flickering in and out of existence almost instantaneously, emitting tremendous radiation as it evaporates. In fact, its Hawking radiation would be so intense that it would evaporate in a fraction of a Planck time. This brings us to another way of understanding the Planck length. It's not just the scale where quantum gravity becomes important. It's also the scale where spacetime itself might be fundamentally grainy. Imagine zooming in on the fabric of spacetime at the Planck scale. What would you find? Some physicists, following ideas developed by John Wheeler, suggest you'd find what's called the quantum foam. Space wouldn't be smooth and continuous at these scales. Instead, it would be a seething, bubbling cauldron of virtual particles constantly popping into and out of existence. Space-time itself would fluctuate wildly. The geometry of space would twist and contort. Tiny wormholes might connect distant regions. The very distinction between space and time might blur. This quantum foam is not mere speculation. It emerges naturally from the mathematics of quantum field theory when you carefully examine what happens at scales near the Planck length. Virtual particles, particles that exist for incredibly brief moments due to quantum uncertainty, would be energetic enough at these scales to bend spacetime itself. The structure of space would be fundamentally uncertain, fluctuating billions of times per second. Yet these fluctuations would only be significant at the Planck scale. At larger scales, all these quantum fluctuations would average out, leaving smooth classical spacetime. Let's take a breath and think about the implications. If spacetime is truly grainy at the Planck scale, then space and time might not be infinitely divisible after all. There would be a smallest unit of spacetime, a quantum of space and time, just as light comes in quanta called photons. Some physicists have proposed calling these units chronons, units of time, or spacons, units of space, though these terms remain speculative. But the idea is powerful. Just as matter is made of atoms, which are made of electrons and nuclei, which are made of quarks and gluons, perhaps space and time themselves are made of more fundamental building blocks. This raises a profound question. If space-time is quantized, if it comes in discrete units at the Planck scale, then what is space and time made of? What is the more fundamental layer of reality from which space-time emerges? This is one of the central questions driving research in quantum gravity. Different approaches offer different answers. String theory, for instance, proposes that the fundamental objects in the universe are not point particles, but tiny vibrating strings. These strings are so small, on the order of the Planck length, that we perceive them as point particles. Different vibrational modes of the strings correspond to different particles. Gravity, in string theory, emerges naturally from one particular vibrational mode. The strings exist in more dimensions than the 3 spatial dimensions and one time dimension we perceive. There are 6 or 7 additional dimensions, curled up and hidden at scales around the Planck length. Loop quantum gravity takes a different approach. Rather than starting with strings, it starts with spacetime itself. It treats spacetime as a quantum object, similar to how quantum mechanics treats other objects. The result is that spacetime is not continuous. It's woven from loops of quantum geometry, connecting to each other at nodes. Space has a discrete structure at the Planck scale, composed of tiny loops with characteristic size around the Planck length. Time is also quantized. It comes in discrete steps of Planck time. Both of these approaches, while very different, share a common insight. At the Planck scale, space and time are not what they seem at larger scales. They're not fundamental. They're emergent phenomena, arising from deeper structure. This is a revolutionary idea. For centuries, space and time have been treated as the stage on which physics occurs. They're the backdrop, the container in which all other phenomena take place. But at the Planck scale, space and time take center stage. They become players in the drama, subject to the same quantum rules as everything else. Not just does the Planck length set a scale for space-time structure, it also sets a scale for other physical phenomena. For instance, the wavelength of a particle is inversely related to its momentum. A particle with very high momentum has a very short wavelength. The Planck length is roughly the wavelength that a particle would have if it had as much momentum as possible without creating a black hole. At that scale, both quantum and gravitational effects are equally important. Similarly, the Planck mass is the mass of an object that would have the Planck length as its Schwarzschild radius, the radius at which it would become a black hole. This mass is about 22 micrograms, similar to the mass of a grain of sand. It seems strange to call this a tiny mass. It's much larger than an atom. But in the context of particle physics, it's extraordinarily large. No elementary particle has anywhere near this mass. The heaviest elementary particles we know of are the top quark and the W and Z bosons, each with a mass around 100 times larger than a proton. But even these are trillions of times lighter than the Planck mass. This dramatic difference between the Planck mass and the mass of elementary particles is called the hierarchy problem, and it's one of the great mysteries of modern physics. Why is gravity so much weaker than the other forces? Why is the gravitational force scale, set by the Planck mass, so far removed from the weak force scale, set by the mass of the W and Z bosons? Some physicists suspect that extra dimensions or other hidden structure might hold the answer. Others wonder if there's new physics waiting to be discovered at intermediate scales between the weak force scale and the Planck scale. The Planck length also provides a natural unit of measurement for quantum gravity calculations. Many theoretical physicists work in Planck units, where the Planck length, Planck time, Planck mass, and other Planck quantities are all set equal to 1. This greatly simplifies the mathematics. When you do this and look at quantities in terms of Planck units, You can often see the structure of physical laws more clearly. Consider this. If you took all of the matter and energy in the observable universe and compressed it to the size of the Planck length, the density would be incomprehensibly enormous. It would be roughly the Planck density, the density of the universe at the moment of the Big Bang. This is one reason why understanding the Planck scale is crucial for understanding cosmology. To comprehend how the universe began, we need a theory of physics that works at the Planck scale. And here's something to gently contemplate. We are, in a sense, made of physics that occurs at scales far removed from the Planck length. The atoms in your body are about 10 to the negative 10 meters across. That's about a billion times larger than the Planck length. Your neurons, your thoughts, your consciousness, all of these emerge from the interaction of countless atoms, operating according to quantum mechanical rules at scales many orders of magnitude larger than the Planck scale. And yet, the Planck scale is still there, still fundamental, still shaping the laws that govern your atoms. In a deep sense, the Planck scale is written into your very being. The Planck length represents one of the most profound insights of theoretical physics, the recognition that space itself has structure, that space and time are not infinitely smooth and continuous, and that at the deepest levels of reality, new physics awaits. We've only begun to peer past the veil that hides the Planck scale from direct observation. But as our understanding deepens, the Planck length looms larger and larger as a fundamental boundary, not a barrier to understanding, but a gateway to a deeper comprehension of the universe's deepest secrets. Now let's turn our attention to time itself. Just as there appears to be a smallest possible distance, the Planck length, there seems to be a smallest possible interval of time. This is the Planck time, and it opens a window onto one of the most profound moments in cosmic history. The Planck time is calculated much like the Planck length. You take Planck's constant, the speed of light, and the gravitational constant, combine them in a specific mathematical way, and out emerges a time interval, approximately 539 times 10 to the negative 44 seconds. To grasp how short this is, consider this. The age of the universe is about 13.8 billion years. In seconds, that's roughly 4 times 10 to the 17 seconds. The ratio between the age of the universe and the Planck time is comparable to the ratio between the age of the universe and a single second. The Planck time is to 1 second what 1 second is to the entire age of the cosmos. Let's pause and breathe. These numbers are so extreme that our minds struggle to hold them. But this struggle itself is informative. It tells us we're approaching the very edge of what's knowable, the frontier where physics itself transforms into something new. The Planck time holds special significance because it defines a temporal boundary, just as the Planck length defines a spatial boundary. Events separated by less than the Planck time cannot causally influence each other, according to the principles of quantum mechanics and relativity combined. This is because information cannot travel faster than light, and at the Planck scale, the distance light travels in 1 Planck time is exactly 1 Planck length. So you cannot have a cause and effect separated by a smaller time interval or smaller distance. The Planck time is the smallest meaningful interval of time in the universe. This has extraordinary implications for our understanding of time itself. In your everyday experience, time seems to flow continuously. You perceive time as smooth, unbroken, infinitely divisible. You can think of any moment you want. Noon, 12:01, 5, half a second past noon. 12:1, or any finer subdivision. But at the Planck scale, this smooth flow of time might cease to exist. Time might be quantized, broken into discrete chunks of Planck time, like a motion picture made of individual frames. Below this scale, time might not exist as we understand it at all. Imagine you're watching a film projected on a screen. At normal viewing distances, the motion appears smooth and continuous. But if you examine the film itself, you discover it's made of individual frames, each frozen in time. The illusion of continuous motion emerges from the rapid succession of discrete frames. Some physicists suspect that time itself might work similarly. What we perceive as continuous time might actually be composed of discrete moments, each lasting one Planck time, strung together so rapidly that we perceive smooth, continuous flow. This leads to a remarkable possibility. Time might not be fundamental. Just as space-time can be curved and warped by gravity, perhaps time itself can fluctuate and change at the Planck scale. At larger scales, time averages out into something smooth and predictable. But at Planck scales, time becomes uncertain, grainy, subject to quantum fluctuations. The very distinction between past, present, and future might blur. Multiple time directions might exist simultaneously. Causality itself might become probabilistic rather than deterministic. You might think that time's fundamental nature is a philosophical question, removed from the realm of practical physics. But actually, the nature of time at the Planck scale has profound implications for cosmology, the study of the universe's origin and evolution. It bears directly on one of the deepest questions: how did the universe begin? According to modern cosmology, the universe began in an event we call the Big Bang. The entire observable universe, all the matter, energy, space, and time that exists, erupted into being from an infinitesimal point of unimaginable density and temperature. But what does began mean? What came before? Did time itself have a beginning? These questions touch on the boundary of what we can know. Our current theories of physics break down at the moment of the Big Bang. General relativity predicts that spacetime becomes infinitely curved at that moment. The density becomes infinite. The temperature becomes infinite. These infinities are signs that our theory has reached its limit. They're telling us that we need a better theory, a theory of quantum gravity, to understand what truly happened at the universe's origin. The Planck time is intimately connected to this cosmic beginning. According to current theories, the universe became opaque to our observations at a time of about 1 Planck time after the Big Bang. Before this moment, the universe was so hot and dense that no meaningful structure could exist. Photons couldn't travel far without being absorbed. Space and time were so wildly curved by gravity and so violently fluctuating due to quantum effects that our normal concepts ceased to apply. From the Big Bang to 1 Planck time. This is the realm of quantum gravity, where our understanding becomes fuzzy and uncertain. In this extraordinarily brief interval, the entire future history of the universe was, in some sense, written. The initial conditions set at this moment determined how the universe would expand, cool, and evolve. Yet we have no direct access to this era. We cannot observe it. We can only infer it through theoretical reasoning and by studying the universe as it appears today. Let's drift gently through what might have happened in that first Planck time. The universe was a seething foam of quantum fluctuations, where virtual particles constantly popped into and out of existence. Space and time themselves were fluctuating wildly, with no clear distinction between the two. Gravity was as strong as the other fundamental forces, not the weak, negligible force it is today, but a powerful interaction comparable in strength to electromagnetism and the nuclear forces. Perhaps all 4 fundamental forces were unified into a single superforce at this moment. As the universe expanded, it cooled. Fractions of a second after the Big Bang, this unified force would have split apart into the 4 separate forces we know today. Gravity broke away first, becoming the weak force we know now. Then the strong and weak nuclear forces separated. And finally, in the first fraction of a millionth of a second, electromagnetism and the weak force would separate into their distinct forms. Each of these symmetry-breaking events would have released enormous amounts of energy, shaping the structure of matter and energy that would eventually lead to atoms, stars, galaxies, and ultimately to, you and me. But all of this, the inflation of space, the cooling of the universe, the emergence of particles and forces, is predicated on our understanding of space-time. And at the Planck scale, our understanding breaks down. We don't know if time itself is fundamental or emergent. We don't know if space is continuous or discrete. We don't know if causality operates the way we think it does. These are open questions at the frontier of physics. Take a breath. Let's consider another implication of the Planck time. If time is truly quantized, broken into discrete units of Planck time, then the universe has a kind of temporal resolution limit, like the pixel size of a digital image. You cannot measure time more precisely than this. You cannot observe events separated by less than one Planck time. This has profound implications for quantum mechanics itself. In quantum mechanics, there's something called the time-energy uncertainty principle. It's similar to the more famous position-momentum uncertainty principle. Just as you cannot simultaneously know a particle's exact position and exact momentum, you cannot simultaneously know a particle's energy and the time at which you measured that energy. The more precisely you measure the time, the more uncertainty arises in the energy measurement. This fundamental uncertainty in time arises from quantum mechanics. But here's the subtle point. If there's a minimum resolvable time interval, the Planck time, then there's also a maximum energy that can be confined to any region of space for any period of time. At the Planck scale, this maximum energy becomes equal to the energy required to create a black hole of that size. This provides a natural cutoff to the infinities that plagued early attempts to combine quantum mechanics and gravity. It's as if nature itself is saying, here is where things get complicated. Here are the real limits. The Planck time also defines something called the Planck epoch, the earliest period in the history of the universe, from time zero, the Big Bang, to one Planck time later. During this epoch, the universe was so hot and dense that quantum gravitational effects were the dominant force shaping its behavior. We know almost nothing about this epoch from direct observation. It's hidden behind what physicists call the veil of quantum gravity. No information can travel from inside this epoch to the present day, so we cannot see it directly. Yet despite this barrier, physicists have developed speculative theories about what might have happened during the Planck epoch. Some propose that the universe underwent cosmic inflation, a period of exponentially rapid expansion that began during or just after the Planck epoch. Others suggest that time itself might have been different then, flowing in multiple directions, or existing in a state of quantum superposition. Still others wonder if our universe is one of many, born from quantum fluctuations in an earlier, even more fundamental, reality. One fascinating proposal comes from a physicist named James Hartley and Stephen Hawking. They suggested that in quantum gravity, the concept of time might be fundamentally different at the Big Bang. They proposed what they call the no-boundary proposal, the idea that the universe has no boundary in time. In this view, the universe doesn't have a moment of creation in the usual sense. Instead, space-time is finite in extent, but has no boundaries, much like the surface of a sphere. You can travel around the surface of a sphere indefinitely, without encountering an edge or boundary. Similarly, space-time might curve back on itself in the time direction, so that there is no first moment of time, no initial singularity. The universe simply is, without needing to be created from something else. This is not to say the universe is eternal in the traditional sense, it's subtle. In this framework, asking, what came before the Big Bang, is a bit like asking, what is north of the North Pole? The question itself contains a conceptual error. There is no before the Big Bang, because time itself emerges from the structure of space-time, and space-time has no boundary in time. Not just does the Planck time define the earliest era of the universe. It also defines a horizon for our cosmic knowledge. Because of the finite speed of light and the finite age of the universe, we can only observe a limited region of space. This region is called the observable universe, and it extends about 46 billion light-years in all directions from Earth. Beyond this horizon, the universe continues, but we cannot see it, because light from those regions hasn't had time to reach us yet. But there's another horizon, even closer and even more fundamental, the Planck horizon. This is defined by the Planck time and the Planck length. just as the size of the observable universe is roughly the speed of light multiplied by the age of the universe. The Planck horizon is roughly the speed of light multiplied by the Planck time, which equals the Planck length. This is the smallest scale at which causality is preserved. Below this scale, causality becomes fuzzy and uncertain. This Planck horizon surrounds every point in spacetime, limiting how much information can be contained within it. This connects to deep ideas in quantum information theory and black hole thermodynamics. The physicist Juan Maldacena discovered a remarkable connection between gravity in a curved spacetime and quantum field theory on a lower dimensional boundary. This connection, called the AD-S-CFT correspondence, suggests that a higher dimensional theory of gravity might be equivalent to a lower dimensional quantum field theory. In this framework, space itself emerges from information encoded on a lower dimensional surface, with the Planck length setting the fundamental scale of this encoding. Here's something beautiful to gently contemplate. The Planck time connects the microscopic world of quantum mechanics to the cosmic scale of the universe's entire history. The ratio between the Planck time and the age of the universe is extraordinarily small. But this ratio is a kind of cosmic constant, reflecting deep relationships between fundamental physical constants. The fact that these constants have the values they do is one of the great mysteries of physics. Why is the speed of light approximately 300,000 kilometers per second? Why does the gravitational constant have the value it does? Why is Planck's constant so small? The answers might involve deep structure that we haven't yet discovered, perhaps additional dimensions, supersymmetry, or other exotic physics waiting to be uncovered. The Planck time also reminds us of a profound truth. Time is not what it seems. From our everyday perspective, time is an arrow pointing from past to future, flowing at a constant rate. But relativity teaches us that time is relative, flowing at different rates depending on speed and gravity. And quantum mechanics teaches us that time is uncertain, subject to fundamental limits on how precisely it can be measured. At the Planck scale, these lessons reach their culmination. Time is not a simple fundamental thing. It's woven together with space into spacetime, subject to quantum uncertainty, capable of fluctuating and warping in ways we're only beginning to understand. And yet, despite all this strangeness and uncertainty, time persists as one of the most fundamental aspects of reality. The universe evolves in time. Causes precede effects. Energy is conserved. The laws of physics are written in terms of how things change in time. Understanding the Planck time, this smallest meaningful interval of time, brings us closer to understanding the universe's deepest secrets. It brings us to the threshold where time itself begins to transform into something new, something we've yet to fully comprehend. Let's settle in and explore something truly remarkable. At the Planck scale, space-time itself becomes strange and uncertain. It transforms into what physicists call quantum foam, a seething, bubbling sea of virtual particles and quantum fluctuations that exists at the very foundation of reality. To understand quantum foam, we first need to understand virtual particles. In quantum mechanics, particles don't exist in isolation. They're surrounded by clouds of other particles constantly popping into and out of existence. These are virtual particles, and they're not merely theoretical constructs. They have real, measurable effects. The Casimir effect, for instance, demonstrates that virtual particles have genuine physical consequences. When two uncharged metal plates are placed very close together in a vacuum, the fluctuations of virtual particles between the plates create a measurable force pushing the plates together. It's as if the quantum vacuum itself is active, alive with possibility. At normal scales, these virtual particle fluctuations are incredibly brief and fleeting. A virtual particle might blink into existence for a billionth of a trillionth of a second before annihilating with its antiparticle. The energy required to create this particle-antiparticle pair is borrowed from the quantum vacuum, repaid almost instantaneously due to the uncertainty principle. These events are so rapid and so small that we don't normally notice them. They average out to nothing on larger scales. But at the Planck scale, everything changes. The quantum fluctuations become so energetic and so violent that they begin to affect the geometry of spacetime itself. Each virtual particle, with its mass and energy, curves spacetime according to Einstein's equations. At Planck scales, this curvature becomes so extreme and so chaotic that spacetime loses its smooth, classical character. It becomes grainy, it fluctuates wildly, it transforms into quantum foam. Imagine spacetime as an ocean. At large scales, the scales of everyday experience and even cosmic scales, this ocean appears smooth. You can measure the exact height of the water at any point. You can predict how waves will propagate. The surface has a well-defined geometry. But zoom in to the Planck scale, and this smooth ocean reveals its true nature. It's not truly smooth at all. It's made of countless quantum fluctuations, each one creating tiny waves and ripples. Virtual particles are constantly emerging from the foam and disappearing back into it. The geometry of spacetime is uncertain, fluctuating billions of times per second. At these scales, spacetime develops a kind of texture or grain. You might imagine spacetime as being woven from incredibly tiny threads, each with a characteristic size around the Planck length. Or you might picture it as being pixelated, like a digital image, with each pixel representing a quantum of spacetime. Different theoretical approaches suggest different pictures, but they all converge on the same basic idea. At the Planck scale, spacetime is fundamentally discrete, not continuous. One particular feature of quantum foam that fascinates physicists is the possibility of tiny wormholes. A wormhole is a connection between two distant regions of spacetime, like a tunnel through space. In principle, Einstein's equations allow for wormholes, but they're incredibly unstable. For a macroscopic wormhole to exist for any appreciable time, you'd need exotic matter with negative energy density, something we've never observed and may not exist. However, at the Planck scale, virtual wormholes might constantly form and collapse. These are called Planck wormholes or Planck wormholes, and they would be so tiny and so ephemeral that they wouldn't affect the large-scale structure of spacetime. But collectively, across the vast expanse of quantum foam, they might have subtle effects on how spacetime behaves. Take a breath. This is where things get genuinely strange. If spacetime is made of quantum foam at the Planck scale, with virtual particles and wormholes constantly appearing and disappearing, then what does this mean for our understanding of space and time? It suggests that space and time, which have always been treated as fundamental aspects of reality, might actually be emergent phenomena. They might arise from something more basic, something more fundamental than spacetime itself. This is a revolutionary idea. For centuries, space and time were considered the fixed stage on which the drama of physics unfolds. Everything else, particles, fields, forces, existed within space and time. But quantum gravity suggests that space and time themselves are players in the drama. They can fluctuate, they can be created and destroyed. They're subject to quantum uncertainty, just like everything else. Several theoretical approaches explore how spacetime might emerge from more fundamental structures. Loop quantum gravity, developed by physicists like Carlo Rovelli and Lee Smolin, proposes that spacetime is woven from loops of quantum geometry. These loops connect at nodes, forming a network. This network has a discrete structure at the Planck scale. Space isn't a smooth continuum, but rather a quantum superposition of many different network configurations. As you zoom out to larger scales, these networks average together to create the smooth, classical spacetime we perceive. Another approach comes from string theory. In string theory, the fundamental objects aren't particles or even fields, but tiny vibrating strings. These strings exist in many dimensions, typically 10 or 11. The extra dimensions are curled up at the Planck scale, hidden from our direct observation. Spacetime, in this framework, emerges from the vibrations and interactions of countless strings. Gravity arises naturally from one particular vibrational mode of the strings. Causal dynamical triangulation is yet another approach. It's based on a simple idea. Spacetime might be made up of tiny, discrete building blocks called simplices. These are the simplest possible geometric shapes: triangles in 2 dimensions, tetrahedra in 3 dimensions, and higher dimensional analogues in more dimensions. At the Planck scale, spacetime would be a foam of these simplices, constantly rearranging themselves according to quantum rules. As you zoom out, these microscopic geometric units combine to create the smooth, continuous spacetime of general relativity. Asymptotic safety is a different proposal, suggesting that gravity might become asymptotically safe at very high energies. This is a technical term, meaning that the coupling constant of gravity, the parameter that determines gravity's strength, approaches a fixed value at high energies rather than running off to infinity. If true, this would provide a natural way to regularize quantum gravity and avoid the infinities that plagued earlier attempts. What's remarkable is that all these different approaches, despite their differences, seem to converge on similar conclusions about the Planck scale. They all suggest that spacetime is not smooth and continuous at Planck scales. They all point toward some kind of discrete, grainy structure underlying classical spacetime. They all indicate that quantum fluctuations in spacetime geometry are significant at these scales. You might wonder whether any of this can be tested experimentally. After all, we cannot directly observe the Planck scale. Our best particle accelerators can probe scales millions of times larger. How could we ever hope to see evidence of quantum foam or the discrete structure of spacetime? The answer lies in looking for subtle effects and indirect signatures. Some physicists have proposed that quantum foam might cause a kind of foaming of spacetime at astronomical distances. This would be a very small effect, but it might be detectable through careful observations of distant objects. For instance, if spacetime is fundamentally grainy, then the light from distant sources might be slightly blurred or distorted as it travels through this grainy structure. This blurring would accumulate over billions of light years, potentially creating observable effects. Astronomers have searched for such effects using gamma-ray bursts and other distant high-energy phenomena. So far, no definitive evidence has been found, but the search continues. Some experiments, like the Fermi Gamma-Ray Space Telescope and newer gravitational wave detectors, are sensitive enough to potentially detect quantum gravity effects if they're large enough. Another approach involves looking at the cosmic microwave background, the ancient light that was released about 380,000 years after the Big Bang, when the universe became transparent to radiation. This light carries imprints of the conditions that existed in the early universe. If quantum gravity effects were significant in the very early universe, they might have left subtle signatures in the temperature fluctuations of the cosmic microwave background. Scientists carefully analyze these fluctuations, searching for patterns that might hint at quantum gravity. Black holes offer another window into quantum gravity effects. When Stephen Hawking discovered that black holes emit radiation due to quantum effects near the event horizon, it opened a new way to think about quantum gravity. The radiation comes from virtual particle pairs being created near the event horizon, with one particle falling into the black hole and the other escaping as Hawking radiation. This process is intimately connected to quantum foam and virtual particles. The study of black hole thermodynamics and information paradoxes continues to yield insights into the nature of quantum gravity. Here's something to gently ponder. If spacetime is emergent, arising from quantum foam and discrete building blocks at the Planck scale, then what does this mean for our intuitions about space and time? It suggests that the continuity and smoothness we perceive are illusions, beautiful, useful illusions created by averaging over countless discrete quantum events. Just as a video appears to show continuous motion but is actually made of discrete frames, spacetime appears continuous but is actually composed of discrete quanta. This raises philosophical questions as well as physical ones. If spacetime is emergent, then in some sense, Space and time don't truly exist at the most fundamental level. They're helpful concepts, useful ways of organizing our understanding of the universe. But at the deepest level, the universe might be fundamentally atemporal and non-spatial. It might be made of something that has neither space nor time as intrinsic properties. Space and time would emerge only at larger scales, when we're far enough from the Planck scale that quantum fluctuations average out. Some physicists, like James Wheeler, have suggested that spacetime might be a kind of superstructure emerging from a more fundamental layer of reality. Wheeler coined the term quantum foam and spent much of his career contemplating what might underlie spacetime. He proposed that at the Planck scale, spacetime might be so curved and twisted that the very concepts of space and time cease to have meaning. Instead, what exists at the most fundamental level might be pure information, quantum information, describing the state of reality without reference to space or time. This connects to the holographic principle, an idea that emerged from studies of black holes and quantum gravity. The holographic principle suggests that all the information contained in a volume of space might be encoded on its boundary, a lower dimensional surface. In this view, the three-dimensional universe we perceive is a holographic projection of information stored on a two-dimensional surface. The Planck length would set the fundamental scale of this encoding, the size of the smallest pixels on the holographic screen. Imagine a hologram, the kind you might see in science fiction films. The entire three-dimensional image is encoded in a two-dimensional pattern of light and dark. From different angles, you see different aspects of the image, but all the information is contained in that two-dimensional pattern. The holographic principle suggests that our universe might work similarly. With the three-dimensional space and time we experience being a projection of information encoded on a distant two-dimensional surface at scales around the Planck length, the implications are staggering. If this is true, then reality is fundamentally different from what we perceive. What we experience as three spatial dimensions plus time might be a projection of a lower dimensional reality. Our sense of being located in space might be a useful fiction. We might be, in a sense, experiences encoded in the quantum state of a lower dimensional universe. Not just is quantum foam strange in its structure, it's also strange in its properties. Because of quantum uncertainty, the geometry of spacetime would be uncertain. This doesn't mean we simply don't know the geometry. It means the geometry itself is in a state of quantum superposition. Every possible geometry is realized with some probability. At larger scales, these different geometries would average together to create the unique, classical spacetime we observe. But at Planck scales, all possibilities coexist. This quantum superposition of geometries has profound implications. It means that at the Planck scale, there might not be a definite answer to questions like, what is the distance between 2 points? Or, how much time has passed? Instead, there would be a probability distribution of possible distances and times. The universe would be fundamentally uncertain, probabilistic, alive with unrealized possibilities. Yet somehow, from this quantum foam of uncertainty and virtual particles and fluctuating geometry, a classical universe emerges. Matter and energy congeal into particles and fields. Spacetime settles into a relatively smooth, predictable geometry. Stars form, galaxies form, life emerges, and eventually, conscious beings arise who can contemplate the quantum foam from which they arose. It's a stunning chain of emergence, each level arising from more fundamental layers beneath. Let's pause for a moment and appreciate the beauty of this vision. The universe, at its deepest level, is woven from quantum uncertainty and probability. It's fundamentally strange and unknowable at the Planck scale. Yet from this strange foundation, a universe of breathtaking beauty and complexity emerges. Mountains and oceans, stars and galaxies, plants and animals, all arising ultimately from the quantum foam. You and I, with our thoughts and feelings and dreams, arising from the same quantum substrate. It's humbling and wondrous all at once. The quantum foam awaits our deeper understanding. As our theories of quantum gravity continue to develop, as our experiments become more sophisticated, we may eventually unveil the true nature of this quantum substrate. We may discover that spacetime is indeed discrete, grainy, made of Planck-scale building blocks. Or we may discover something even stranger, something that current theories haven't even contemplated. But whatever we find, it will surely deepen our appreciation for the profound mystery at the heart of reality. Now let's drift gently into one of the most profound mysteries at the intersection of quantum mechanics and gravity, black holes, and the puzzle of what happens to information when matter falls into them. This mystery has profoundly shaped our understanding of the Planck scale. A black hole is a region of space-time so densely packed with matter or energy that nothing, not even light, can escape its gravitational pull once it crosses a boundary called the event horizon. At the center of a black hole lies what's called a singularity, a point where space-time curvature becomes infinite according to general relativity. The black hole itself is invisible because no light can escape from within the event horizon. We can only detect black holes by observing their effects on nearby matter and radiation. Black holes have fascinated physicists ever since Einstein published his theory of general relativity. They seemed like mathematical curiosities, probably too exotic to exist in nature. But in the decades following Einstein's work, astronomers discovered that black holes are actually quite common. Most galaxies, including our own Milky Way, contain supermassive black holes at their centers. Black holes form when massive stars collapse at the end of their lives. And in the early universe, smaller black holes might have formed directly from regions of high density. For a long time, black holes were considered objects from which nothing could ever escape. They were perfect prisons, bottomless pits of gravity. But in 1974, Stephen Hawking made a revolutionary discovery. He showed that black holes aren't truly black. They emit radiation due to quantum effects near the event horizon. Here's how Hawking's discovery works. Near the event horizon of a black hole, quantum effects become significant. Virtual particle pairs are constantly being created out of the quantum vacuum. Normally, these pairs annihilate almost immediately, leaving no trace. But near a black hole's event horizon, something remarkable can happen. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real radiation that travels away from the black hole. The infalling particle, having negative energy relative to infinity, reduces the black hole's mass. The net result is that the black hole appears to radiate energy, slowly evaporating over time. This Hawking radiation is extraordinarily faint for stellar mass black holes. A black hole with the mass of the Sun would emit radiation at a temperature of only a millionth of a degree, much colder than the cosmic microwave background. So such a black hole would actually absorb more radiation from the universe than it emits. But smaller black holes would radiate more intensely. A tiny black hole with the mass of a mountain would glow brilliantly and evaporate in a flash of radiation. And a black hole at the Planck scale, with the Planck mass and the Planck length as its size, would have an extraordinarily short lifetime, evaporating in about 1 Planck time. This is where the Planck scale enters our discussion of black holes. The smallest possible black hole, according to general relativity, would have a radius of about 1 Planck length and a mass of about the Planck mass. It would be on the absolute edge of what can be called a black hole. Smaller than this, and the object wouldn't be a black hole at all. It would be something else, governed by quantum mechanics. This Planck scale black hole represents a natural quantum of gravity, the smallest possible black hole that could theoretically exist. Take a breath. Now we reach the heart of the paradox. Hawking's discovery raised a troubling question. What happens to the information contained in matter that falls into a black hole? If you throw a book into a black hole, the book is destroyed. It crosses the event horizon and reaches the singularity. But the information encoded in that book, the arrangement of its atoms, the meaning of the words, doesn't simply vanish from the universe. Or does it? In quantum mechanics, information is never destroyed. This is a fundamental principle. The quantum state of the universe evolves deterministically according to the Schrödinger equation. In principle, if you knew the complete quantum state at one moment, you could calculate the quantum state at any other moment, past or future. This is called unitarity. But if information is destroyed by falling into a black hole, then quantum mechanics would be violated. You couldn't track the quantum state of the universe if information is disappearing into black holes. This is the black hole information paradox, and it's been the subject of intense research for decades. Hawking initially suggested that information might be destroyed in black holes, and the universe's quantum state might be fundamentally non-unitary. But this troubled many physicists because it seemed to violate deep principles of quantum mechanics. Others suggested that the information might be preserved in the Hawking radiation itself. Perhaps the radiation emitted as a black hole evaporates contains, in subtle correlations, all the information that fell into it. If true, this would preserve unitarity and allow the quantum state of the universe to remain coherent. But the challenge is that calculating exactly how this information could be encoded in the radiation seems incredibly difficult, perhaps impossible with our current understanding. The resolution to this paradox, many physicists believe, lies in understanding the Planck scale physics more deeply. At the Planck scale, space and time might become so curved and distorted that the very distinction between inside and outside the event horizon becomes fuzzy. Virtual wormholes might connect different regions of spacetime, or spacetime itself might be quantized in such a way that the singularity never truly forms. The information might be preserved through mechanisms we haven't yet discovered, operating at Planck scales where both quantum mechanics and gravity are equally important. This connects to one of the most important ideas in modern theoretical physics, the AD-CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence suggests a deep duality between two very different theories. On one side, there's gravity in a curved spacetime, anti-de Sitter space. On the other side, there's a quantum field theory on the boundary of that spacetime, with no gravity. The correspondence suggests that these two theories are actually describing the same physics, just from different perspectives. What makes this remarkable is that it suggests gravity might emerge from quantum information on a lower dimensional boundary. In this framework, a black hole in the higher dimensional gravitational spacetime might correspond to a highly excited state in the lower dimensional quantum field theory. The information that seems to disappear into the black hole might actually be encoded in this lower dimensional state, preserved according to quantum mechanical principles. You might think that the AD-CFT correspondence is purely abstract, disconnected from the real universe. But it has profound implications. It suggests that space itself might be emergent, arising from quantum entanglement and quantum information. The Planck length might set the fundamental scale of this information encoding. Information, at the deepest level, might be more fundamental than space or time. Not just is the black hole information paradox important for understanding quantum gravity, it also connects to the second law of thermodynamics and the nature of entropy. Entropy is a measure of disorder, or equivalently, the number of microscopic states consistent with a macroscopic configuration. The second law of thermodynamics states that entropy always increases over time. In a closed system, disorder tends to grow, but black holes seem to violate this law. When matter with lots of disorder falls into a black hole, the disorder seems to disappear. The event horizon hides the disorder from the outside universe. This appears to decrease the total entropy of the universe. Hawking and Bekenstein resolved this paradox by showing that black holes have entropy. The entropy of a black hole is proportional not to its volume, but to its surface area, specifically the area of its event horizon. When matter falls into a black hole, the black hole's entropy increases by more than the entropy lost when the matter disappears. the total entropy of the universe continues to increase, preserving the second law. The entropy of a black hole is remarkably small for a stellar mass black hole. But for a tiny black hole at the Planck scale, the entropy is on the order of 1 bit of information. A Planck scale black hole might represent the fundamental quantum of information in the universe. Everything larger than a Planck scale black hole would contain multiple bits of information. Everything smaller wouldn't be able to exist as a distinct entity. It would be part of the quantum foam itself. This connects to the holographic principle we mentioned earlier. The holographic principle states that the information contained in a volume of space is bounded by the area of its surface, measured in Planck units. Specifically, the information cannot exceed 1 bit per Planck area unit. This principle emerged from studies of black hole thermodynamics and quantum gravity. It suggests that space itself is not fundamental, but emerges from information encoded on a lower dimensional surface. Here's something remarkable to gently contemplate. According to the holographic principle, the entire observable universe, all the matter, energy, and space-time spanning billions of light-years, might be encoded on a 2-dimensional surface with an area measured in Planck lengths. Our 3-dimensional experience would be a projection of this 2-dimensional information. The Planck length isn't just a scale at which gravity becomes quantum. It's the fundamental unit of information encoding. It's the pixel size of reality itself. Let's pause and consider what this means. If the holographic principle is correct, then the universe is fundamentally 2-dimensional, not 3-dimensional, at the Planck scale. What we perceive as 3 spatial dimensions plus time is actually a projection of information encoded on a more fundamental 2-dimensional surface. Our sense of being inside a 3-dimensional space is an emergent property, arising from the quantum state of this 2-dimensional system. This seems to conflict with our everyday experience. We perceive ourselves as existing in 3 spatial dimensions. We can move forward, backward, left, right, up, and down. But if the holographic principle is true, these 3 dimensions are emergent. At the most fundamental level, the information describing everything we see, everything we are, is encoded in fewer dimensions. Yet this isn't as strange as it might seem. Think about how a television works. A 2-dimensional image on the screen appears 3-dimensional to our brain. We perceive depth and motion and realize that these are projections of 3-dimensional reality encoded in a 2-dimensional pattern. The holographic principle suggests the universe works similarly, but in reverse. A 2-dimensional pattern of information encodes our entire 3-dimensional universe. We are holograms in the deepest sense. The study of black holes and the information paradox has profoundly transformed our understanding of quantum gravity and the Planck scale. It has revealed deep connections between thermodynamics, quantum mechanics, and gravity. It has suggested that information might be more fundamental than space or time. And it continues to guide theoretical physicists as they search for a deeper understanding of reality. Black holes themselves remain mysterious in many ways. We don't fully understand what happens at the singularity, where space-time curvature becomes infinite. General relativity predicts a singularity, but the theory is almost certainly incomplete at this point. A theory of quantum gravity might reveal that singularities don't actually exist, that at Planck scales, quantum effects prevent the formation of true singularities. Instead, matter might bounce or be transformed into something entirely different at the Planck scale. Recent work has suggested intriguing possibilities. Some physicists propose that the singularity might be replaced by a bridge or wormhole to another universe. Others suggest that information might be stored in subtle quantum correlations in the Hawking radiation in ways we're only beginning to understand. Still others work on mathematical frameworks, like loop quantum gravity, that might naturally prevent singularities from forming. Each of these ideas points to a common theme. At the Planck scale, where quantum gravity becomes important, the universe behaves in ways that are radically different from what general relativity alone would predict. Black holes become laboratories for studying quantum gravity. They're cosmic experiments that nature is constantly running, revealing hints about the deepest structure of reality. And at the heart of all this is the Planck scale, the scale where space and time become uncertain, where quantum fluctuations dominate, where information might be encoded more fundamentally than space itself. Black holes, far from being simple objects governed only by general relativity, are intimately connected to this Planck scale physics. They're windows into the deepest mysteries of the universe. Now, let's explore one of the most ambitious theoretical frameworks ever proposed, string theory. This framework offers a radically different perspective on the Planck scale and what might lie beneath the surface of space-time itself. For much of the 20th century, physicists worked with the assumption that the fundamental objects in the universe are point particles, objects with no size or structure, existing at a single point in space. Electrons, quarks, photons, all were treated as mathematical points. This worked remarkably well for developing quantum field theory and understanding particle physics. But it created problems when you tried to combine it with gravity. The infinities that plagued quantum gravity suggested that the point-particle framework might be incomplete. In the late 1960s, physicists studying the strong nuclear force discovered something unexpected. They found that particles could be described as if they were vibrating strings rather than point particles. At first, this seemed like merely a mathematical trick, a convenient way to organize calculations. But gradually, physicists realized this might represent something deeper. What if particles aren't truly point-like at all? What if they're actually tiny, vibrating strings? This idea blossomed into string theory. In string theory, the fundamental objects in the universe are one-dimensional strings, so small that they appear point-like at the scales we can currently observe. Different vibrational modes of the strings correspond to different particles. A string vibrating one way might be an electron. Vibrating another way, it might be a photon. A third vibrational mode might correspond to a graviton, the hypothetical particle that mediates gravitational force. Here's where the Planck scale enters. The size of these fundamental strings is on the order of the Planck length, approximately 10 to the negative 35 meters. Strings this small would behave like point particles at all, scales larger than the Planck length. This is why we haven't detected their string nature directly. We'd need accelerators operating at Planck scale energies to resolve their structure, and such accelerators are far beyond our current technological capability. Take a breath. String theory introduces a remarkable concept: extra dimensions. The mathematics of string theory works most elegantly if spacetime has more dimensions than the four we perceive, 3 spatial dimensions plus time. Most versions of string theory require 10 spacetime dimensions. Some versions, called M-theory, require 11. But we only observe 4 dimensions. Where are the extra dimensions? The answer is elegant. The extra dimensions are curled up and hidden at tiny scales around the Planck length. Imagine a garden hose viewed from far away. It appears to be one-dimensional, a line. But if you zoom in close enough, you see that it's actually 2-dimensional, a line with some thickness. The thickness is a second dimension, but it's so small that you don't notice it from a distance. Similarly, our universe might have 6 or 7 additional spatial dimensions that are curled up so tightly, at scales around the Planck length, that they're invisible to us. This is a stunning possibility. It means that when we zoom into the Planck scale, we might discover that space has more dimensions than we ever imagined. The geometry of space itself might unfold into a richer, higher-dimensional structure. Particles that seem to move in 3 spatial dimensions might actually be traveling in more dimensions, with the motion in the extra dimensions hidden from our view. The shapes of these extra dimensions matter tremendously in string theory. Different configurations of extra dimensions lead to different physics in the 4-dimensional space we observe. The properties of particles, the strengths of forces, the masses of particles. All of these are determined by how the extra dimensions are shaped. In principle, if you knew the exact shape of the extra dimensions, you could predict all the fundamental constants of nature. This is both exciting and humbling. It suggests that the universe might have much more structure than we've realized. But it also raises a troubling question. If there are many possible shapes for the extra dimensions, then there might be many possible universes with different physics. Some physicists have calculated that there might be 10 to the 500 different possible configurations of extra dimensions. Each configuration would lead to a different universe with different laws of physics. This is called the string theory landscape, and it's profoundly unsettling to many physicists. It suggests that the apparent fine-tuning of the universe, the fact that physical constants have just the right values to allow stars, galaxies, and life to form, might not be fine-tuning at all. It might simply be selection bias. We find ourselves in a universe with physics that allows observers, because if the physics were different, there would be no observers to find themselves there. But string theory offers more than just the possibility of extra dimensions. It also offers a potential resolution to the infinity problem in quantum gravity. In point-particle quantum field theory, infinities arise from Feynman diagrams with certain topologies. But in string theory, point particles are replaced by extended strings. Strings have a finite size, on the order of the Planck length. This finite size naturally prevents some of the infinities from arising. String theory appears to be perturbatively finite, meaning that the infinities that plagued earlier quantum gravity theories seem to disappear. String theory also naturally includes gravity. One of the vibrational modes of a closed string corresponds to a graviton, the particle that mediates gravity. This is extraordinary because gravity emerges from string theory without being put in by hand. You don't have to assume gravity exists. It emerges naturally from the theory. This suggests that gravity might be fundamentally unified with quantum mechanics through the string framework. Not just does string theory unify gravity and quantum mechanics, it also offers the possibility of unifying all four fundamental forces. In string theory, all particles, quarks, electrons, photons, gravitons, all of them, are excitations of different vibrational modes of the same fundamental strings. They're all manifestations of the same underlying object. This is a beautiful unification. At Planck scale energies, where all the forces have similar strength, this unification becomes apparent. But at lower energies, as the universe cooled after the Big Bang, the unified force split into the four separate forces we observe today. Let's pause and consider what this means for our understanding of reality. String theory suggests that at the Planck scale, the universe has more structure than we imagined. There are extra dimensions. There are fundamental vibrating strings. All the apparent particles are actually different modes of vibration of these strings. Space itself, at the Planck scale, unfolds into higher dimensions. The distinctions between different types of particles blur. All forces merge into one unified interaction. Of course, string theory remains speculative. It has not yet been directly confirmed experimentally. The energies required to probe string-scale physics are a billion times higher than the energies available in our best particle accelerators. Some physicists have criticized string theory for being untestable in principle. Others argue that it's the only consistent framework we have for combining quantum mechanics and gravity. In recent decades, physicists have found remarkable connections between string theory and other areas of physics. The ADS-CFT correspondence, which we discussed earlier, emerged from studies of string theory. This correspondence suggests that a theory of gravity in a higher dimensional space is equivalent to a quantum field theory on the lower dimensional boundary of that space. This is a profound duality, hinting at hidden structures in spacetime itself. Another remarkable discovery comes from studying D-branes in string theory. D-branes are extended objects on which strings can attach. A point particle is like a string attached to a d-brane of 0 dimensions, a point. A one-dimensional extended object would correspond to strings attached to a one-dimensional d-brane, and so on. D-branes opened up new ways of thinking about quantum gravity and black holes. They suggested that black holes might have a microscopic description in terms of d-branes. String theory also offers intriguing perspectives on cosmology and the Big Bang. If the universe is fundamentally made of vibrating strings in 10 or 11 dimensions, then the Big Bang might not be the true beginning of the universe. Instead, the Big Bang might be a transition or a collision in a higher dimensional space. The universe we observe might be a three-dimensional brane, a kind of membrane, embedded in a higher dimensional space. Other branes might exist elsewhere in these higher dimensions, each with their own universe. This is sometimes called the ekpyrotic universe model. In this model, the Big Bang is caused by two branes colliding in higher dimensional space. The collision releases tremendous energy, creating the hot, dense initial conditions of our universe. The universe then expands and cools, just as in traditional Big Bang cosmology. But the Big Bang isn't the true beginning. It's just a collision event in a higher dimensional landscape. Another scenario, called inflation, emerges naturally from some versions of string theory. Inflation is a period of exponentially rapid expansion that might have occurred in the very early universe, before the more familiar expansion we observe today. During inflation, the universe doubles in size roughly every 10 to the negative 36 seconds. This exponential growth would smooth out irregularities in the universe's density and temperature, providing a natural explanation for why the universe appears so homogeneous on large scales. You might think that string theory and its extra dimensions are purely abstract, disconnected from observational reality. But in fact, string theory makes predictions that could, in principle, be tested. If extra dimensions exist at Planck scales, they might affect gravity in subtle ways that could be detected. The Large Hadron Collider was designed, in part, to search for signatures of extra dimensions. So far, no direct evidence has been found, but the search continues. Some predictions of string theory are indirect. For instance, string theory predicts the existence of supersymmetry, a symmetry relating fermions, matter particles, and bosons, force-carrying particles. If supersymmetry exists, the Large Hadron Collider should have detected superpartners of known particles, particles with properties similar to known particles but with different spin. The fact that these haven't been detected yet suggests either that supersymmetry is realized in nature in a more subtle way, or that string theory might need modification. String theory has also inspired new mathematical frameworks and revealed deep connections between seemingly different areas of mathematics. It has led to developments in topology, geometry, and quantum field theory. Even if string theory turns out not to describe fundamental reality, it has proven to be an extraordinarily fertile source of ideas and mathematical insights. There are alternatives to string theory in the quest to understand quantum gravity. Loop quantum gravity, which we mentioned earlier, takes a different approach. Rather than introducing tiny strings, loop quantum gravity quantizes spacetime directly, treating geometry as a quantum object. In this framework, space is woven from loops of quantum geometry, and spacetime has a discrete structure at the Planck scale. Causal dynamical triangulation is another approach, treating spacetime as built from discrete geometric units called simplices. Asymptotic safety approaches, quantum gravity, by studying the behavior of gravity at high energies. Emergent gravity proposes that gravity might emerge from more fundamental quantum systems, similar to how thermodynamics emerges from the statistical behavior of atoms. Each of these approaches offers different insights into what might happen at the Planck scale. None has yet achieved the level of experimental confirmation we'd like. But collectively, they're painting a picture of reality far richer and stranger than classical physics ever suggested. Here's something to gently contemplate. If string theory is correct, then the universe is far more intricate than our everyday experience suggests. Space has hidden dimensions. Particles are vibrating strings. All forces are unified at Planck scales. The familiar three-dimensional space in which we move is just a thin slice of a much higher dimensional reality. We're like characters living on the surface of a piece of paper, unaware of the three-dimensional world around us. Except in our case, we're living in a three-dimensional or four-dimensional brain, unaware of the higher dimensional space in which our brain is embedded. Yet from this strange multi-dimensional substrate, our universe emerged. Stars and galaxies formed, planets coalesced, life arose, consciousness emerged. And here we are, contemplating the possibility that we might be living in extra dimensions we've never directly perceived. It's humbling and wonderful all at once. Let's shift our perspective now and explore a different framework for understanding quantum gravity. One that doesn't require extra dimensions or vibrating strings, but instead proposes that space-time itself is fundamentally discrete. This approach is called loop quantum gravity, and it offers a distinctly different vision of the Planck scale. Loop quantum gravity emerged in the 1980s and 1990s from the work of physicists like Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and others. Rather than starting with strings or point particles, loop quantum gravity begins with a radical idea. What if we treat spacetime as a quantum object? What if we apply the same principles of quantum mechanics that work so beautifully for particles and fields to spacetime itself? This might seem simple in principle, but it's extraordinarily difficult in practice. General relativity is formulated in a way that makes it resistant to quantization. The mathematical structure doesn't naturally fit into the framework of quantum field theory. For decades, physicists struggled with this problem, but Ashtekar found a clever reformulation of Einstein's equations that made them more amenable to quantization. Using this reformulation, researchers developed loop quantum gravity as a framework for quantum gravity without extra dimensions. In loop quantum gravity, the fundamental objects aren't strings or point particles, they're loops. Imagine spacetime as being woven from tiny loops of quantum geometry, each with a characteristic size around the Planck length. These loops connect to each other at nodes, forming a quantum network. This network represents the quantum state of spacetime. Different arrangements of loops correspond to different geometries of space. Here's where things become beautiful and strange. In loop quantum gravity, space is not continuous. It's quantized. Just as energy comes in discrete quanta, called photons, space comes in discrete quanta, tiny indivisible units of volume. The Planck volume, the smallest possible unit of volume, is roughly the cube of the Planck length. Space is woven from these Planck volume units, just as a tapestry is woven from individual threads. The same is true for area. In loop quantum gravity, area is also quantized. You cannot have a surface with an area smaller than the Planck area. Areas come in discrete multiples of the Planck area. This has profound implications. It means that a black hole's event horizon, which has a definite area, is also made of discrete quanta. The black hole's entropy, which is proportional to the area of its event horizon, is therefore quantized as well. A black hole can have entropy equal to 0, 1, 2, 3, etc. Units of Planck area, but not any fractional value between them. Take a breath. This is a revolutionary idea. In classical geometry, space is infinitely divisible. You can always draw a smaller line segment or a smaller area. But in quantum geometry, there's a fundamental grain to space. You reach a limit when dividing, and that limit is the Planck scale. You might think this discrete structure would lead to problems. Wouldn't a discrete spacetime create discontinuities and lead to infinities in calculations? Remarkably, the opposite seems to be true. The discrete structure of loop quantum gravity naturally avoids many of the infinities that plagued earlier approaches to quantum gravity. It's as if the discrete nature of space prevents certain mathematical pathologies from arising. Not just does loop quantum gravity propose that space is quantized, it also proposes that time is quantized. Just as you cannot have a volume smaller than the Planck volume, you cannot have a time interval smaller than the Planck time. Time comes in discrete steps. each lasting 1 Planck time. This raises profound questions about the nature of time itself. Does time really flow continuously, or does it progress in discrete jumps? When you measure time, are you really measuring a continuous parameter, or are you counting discrete time steps? This connects to an idea proposed long ago by physicist John Wheeler, who called it the problem of time. In quantum gravity, time seems to lose its privileged status as a fundamental parameter. Different approaches to quantum gravity handle time differently. In loop quantum gravity, time becomes something that emerges from the quantum geometry of spacetime, rather than being a fundamental background. In loop quantum gravity, physical evolution is described not by how things change in time, but by how they change as you move through different spatial slices. This is technically called the Wheeler-DeWitt equation. In this framework, the universe doesn't have a unique history. Instead, there's a quantum superposition of all possible histories, weighted by their probability. Asking what happened at a particular moment in time becomes ambiguous. Instead, you ask questions like, what is the probability that a measurement will find this particular configuration of geometry? This is genuinely strange. It means that at the Planck scale, the very notion of history becomes fuzzy and uncertain. The universe doesn't have a definite past. Only when you make a measurement, only when you ask a specific question about the quantum state, does a particular history crystallize. Before measurement, all possible histories coexist in superposition. Let's pause for a moment. What does this mean for our understanding of cosmology and the Big Bang? If time itself is quantized and emerges from quantum geometry, then does the Big Bang make sense as a concept? In classical general relativity, the Big Bang is a singularity, a moment of infinite density and temperature, the beginning of time itself. But in loop quantum gravity, space-time is discrete. There can't be true singularities because space and time are granular. Densities cannot become truly infinite because space is made of Planck volume units. This has led physicists working in loop quantum gravity to propose something remarkable. The Big Bang might not be a true beginning. Instead, the universe might have a quantum bounce. Before the Big Bang, there might have been another universe in a contracting phase. As this universe contracted, it reached a state of enormous density and temperature. But because space-time is quantized, it couldn't contract beyond a certain point. Instead, it bounced. The contraction reversed into expansion, and this is what we observe as the Big Bang. The universe before the bounce would be causally disconnected from our universe after the bounce. We'd have no way of observing it, but it might have existed. This quantum bounce scenario is speculative, but it's supported by calculations using loop quantum gravity. It suggests a universe without a beginning, or at least a universe where the beginning is replaced by a transition. Time itself might extend indefinitely into both past and future, though the nature of time before and after the bounce might be very different. Loop quantum gravity also offers insights into black holes. Remember how we discussed the information paradox, the puzzle of what happens to information when it falls into a black hole? In loop quantum gravity, black holes have a discrete structure at the Planck scale. The event horizon of a black hole is not smooth. It's made of discrete loop quantum geometry woven from Planck length scales. This discrete structure might hold the key to resolving the information paradox. Some physicists working on loop quantum gravity have proposed that the information falling into a black hole might be stored in the discrete structure of the event horizon. The information would be encoded in the quantum geometry at Planck scales. As the black hole evaporates through Hawking radiation, this information would gradually escape, preserving unitarity and the consistency of quantum mechanics. The evaporation process would take an extraordinarily long time for stellar mass black holes, but eventually all the information would be restored. Here's something beautiful to gently ponder. If loop quantum gravity is correct, then the universe is fundamentally a network of interconnected loops. Space is woven from these loops, and time emerges from transitions between different loop configurations. Everything that exists, all matter, all energy, all forces, emerges from the quantum geometry of this loop network. You and I, the atoms in our bodies, the light that allows us to see, all of it would be manifestations of this quantum geometric structure at scales far larger than the Planck scale. We would be, in the deepest sense, made of woven quantum loops. Loop quantum gravity differs significantly from string theory in its approach and implications. String theory requires extra dimensions and additional mathematical structure. Loop quantum gravity works in the four-dimensional spacetime we observe and requires no extra dimensions. String theory treats spacetime as a background on which strings move. Loop quantum gravity treats spacetime itself as a quantum variable. There are also differences in their predictions and testability. String theory predicts extra dimensions and supersymmetry, which so far haven't been directly detected. Loop quantum gravity predicts discrete geometry and quantized area and volume, effects that are subtle and difficult to test directly. However, both approaches might eventually make predictions about phenomena we could observe, perhaps in the cosmic microwave background, or through gravitational wave detection, or other astronomical observations. Other approaches to quantum gravity exist as well. Causal dynamical triangulation, developed by Renate Loll and others, treats spacetime as a quantum superposition of many different discrete geometries, built from elementary geometric simplices. Asymptotic safety, investigated by Steven Weinberg and others, explores the possibility that gravity might have a non-trivial fixed point at high energies, allowing gravity to be renormalizable. Emergent gravity proposals suggest that gravity might emerge from more fundamental quantum systems, much as thermodynamics emerges from statistical mechanics. Each of these approaches reveals different aspects of what might happen at the Planck scale. Some emphasize the discrete nature of spacetime, others focus on quantum foam and uncertainty. Some highlight the role of information, others explore how geometry itself might be emergent. What's remarkable is that despite their differences, these various approaches seem to be converging on some common themes. Almost all serious approaches to quantum gravity suggest that spacetime is not what it appears. Whether it's discrete loops, vibrating strings, D-branes, causal triangles, or something else entirely, the consensus is that at the Planck scale, spacetime has structure and grain that doesn't exist at larger scales. Not just is the structure of spacetime changing in these theories. The very foundations of physics are being re-examined. Space and time, which Newton treated as absolute and unchanging, which Einstein treated as a unified continuum that could be curved and warped, are now being treated as quantum variables, subject to uncertainty and superposition. The distinction between space and time might blur. The number of dimensions might change. The flow of time might become uncertain. This is a genuine revolution in our understanding of nature. We're watching physics undergo a fundamental transformation, comparable to the shift from Newton to Einstein or from classical mechanics to quantum mechanics. The Planck scale is the frontier where this transformation occurs. It's the boundary where our current understanding breaks down and something new emerges. Let's take a moment to appreciate what this means. We live in an age where our understanding of reality is incomplete. We know there's something beyond general relativity and quantum mechanics. We know the Planck scale holds secrets we haven't yet uncovered. And we have multiple frameworks: string theory, loop quantum gravity, causal dynamical triangulation, and others, all attempting to peek behind that veil. The exciting part is that we might be approaching an era where we can actually test these theories. Observations of gravitational waves, the cosmic microwave background, and other astronomical phenomena might eventually reveal signatures of Planck-scale physics. Equipment being developed now might detect subtle effects that could distinguish between different approaches to quantum gravity. The next few decades could bring remarkable breakthroughs in our understanding of reality. In loop quantum gravity, The Planck scale represents not a barrier, but a threshold. It's the point where quantum geometry becomes visible, where the discrete nature of space-time reveals itself. It's where loops of quantum space connect, where time emerges from geometry, where the universe's deepest structure can be glimpsed. And from this Planck scale quantum geometry, the smooth, continuous space-time we experience every day unfolds and emerges, like a vast tapestry woven from infinitesimal threads. Now let's journey backward through time, not to the Planck epoch itself, which remains beyond our reach, but to the earliest moments we can study and understand. Let's explore how Planck-scale physics shaped the universe's infancy and left imprints we can still observe today. The universe began in conditions so extreme that quantum gravity dominated. From the Big Bang to approximately 1 Planck time later, the universe was in the Planck epoch. During this era, temperatures were on the order of the Planck temperature, roughly 10 to the 32 Kelvin. At these temperatures, the energy density was equivalent to the Planck energy density. Every particle had enough energy to create black holes. Space and time were so violently curved by gravity and so wildly fluctuating due to quantum effects that our current theories simply cease to apply. What happened during the Planck epoch? We don't truly know. It's hidden behind a veil of quantum gravity that we haven't yet penetrated. But physicists have developed speculative theories based on our best current understanding of quantum gravity. These theories paint a picture of the universe unlike anything we see today. In these theories, space-time during the Planck epoch was not smooth. It was a seething foam of quantum fluctuations, as we discussed earlier. Virtual particles were constantly popping into and out of existence, each one creating gravitational effects that curved space-time. The distinctions between particles and antiparticles, between different types of particles, might have been blurred. The four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, were all unified into a single superforce, all with approximately equal strength. The universe during this epoch might not have had a well-defined geometry. According to some approaches to quantum gravity, the universe at Planck scales was in a superposition of many different geometries simultaneously. There was no unique spatial arrangement, no definite configuration of space-time. Only when we zoom out to scales larger than the Planck scale, only when quantum fluctuations average together, does a particular geometry emerge, the smooth space-time described by general relativity. Take a breath. This raises a profound question. Did time have a beginning? In classical general relativity, the Big Bang is a singularity where time itself begins. But in quantum gravity, the situation is more subtle. If time is quantized, emerging from quantum geometry, then asking what came before the Big Bang might be like asking what is north of the North Pole. The question contains a conceptual confusion. There might not be a moment of creation in the traditional sense. Instead, the universe might be eternal, with a quantum bounce replacing what would have been a singularity in classical theory. Alternatively, the universe might have begun in a quantum state that was somehow special or unique. The no-boundary proposal by Hartle and Hawking, which we mentioned earlier, suggests that the universe might be finite in extent but have no boundaries, not in space and not in time. The universe would simply exist without needing to have been created from anything. In this view, asking what came before the Big Bang is meaningless because time doesn't extend before that point. After the Planck epoch ended, after the universe was a mere Planck time old, the conditions were still extraordinarily extreme, but now within the realm where our theories might apply. The universe continued to expand and cool. Very quickly, within the first fraction of a second, the unified superforce split into separate forces through a series of symmetry-breaking transitions. First, gravity separated from the other forces. This happened at an energy scale of roughly the Planck energy. Gravity became much weaker than the other forces, as it remains today. This dramatic change in gravity's strength is still mysterious. Why is gravity so much weaker than the other forces? This is the hierarchy problem we mentioned earlier, and it might hint at physics beyond our current theories, perhaps extra dimensions or other hidden structure that becomes apparent at the Planck scale. Next, the strong force separated from the electroweak force. This happened at an energy of roughly 1 trillion times lower than the Planck energy, but still incredibly high by everyday standards. Then, a fraction of a millionth of a second after the Big Bang, the electroweak force split into the electromagnetic force and the weak force. After this point, all four forces operated as distinct entities, as they do today. Throughout this early era, the universe was filled with particles and antiparticles, constantly being created and annihilated in the intense heat. But something remarkable happened early on. There was a slight asymmetry between particles and antiparticles. For every billion antiparticles, there were 1,000,000,001 particles. This tiny difference, a mere 1 part in 1,000,000,000, had enormous consequences. As the universe cooled, most particles and antiparticles annihilated each other, converting to energy in the form of radiation. But that tiny excess of particles, that 1 part in 1,000,000,000 surplus, survived. This surplus is the matter that would eventually form all the stars, galaxies, and life in the universe. Without this tiny asymmetry, the universe would contain only radiation and would never develop the structure necessary for galaxies and life. Where did this asymmetry come from? It might have originated in the Planck epoch, in the quantum foam of the earliest universe. The physics of the Planck scale might have naturally created slightly more particles than antiparticles. This is one tantalizing hint that Planck scale physics has shaped the universe's entire evolution. Let's pause and consider another crucial era, cosmic inflation. Sometime in the first fraction of a second, possibly immediately after the Planck epoch, or possibly a bit later, the universe underwent a period of exponentially rapid expansion called inflation. During inflation, the universe doubled in size roughly every 10 to the negative 36 seconds. In just a tiny fraction of a second, the universe grew from subatomic size to astronomical size. Inflation was proposed in the 1980s by Alan Guth and André Linde to solve several puzzles in cosmology. It naturally explains why the universe is so smooth and homogeneous on large scales. It explains why the curvature of spacetime is so close to flat. It explains the distribution of matter and energy across the universe. And crucially, inflation amplifies quantum fluctuations in the early universe to macroscopic scales, creating the seeds of structure that would eventually grow into galaxies. Here's where the Planck scale becomes essential to cosmology. The quantum fluctuations that inflation amplifies have sizes on the order of the Planck length in the early universe. As inflation proceeds, these tiny quantum fluctuations grow to enormous sizes. By the end of inflation, fluctuations that began at Planck scales have grown to sizes larger than the observable universe. This provides a beautiful explanation for the origin of structure in the universe. The galaxies we observe today, each containing billions of stars, grew from quantum fluctuations at the Planck scale. Not just do Planck scale fluctuations seed the formation of galaxies, they also create the pattern of temperature fluctuations in the cosmic microwave background, the ancient light released 380,000 years after the Big Bang. These temperature fluctuations are incredibly subtle, less than 1 part in 100,000. But they're real, and we can observe them. Satellite missions like WMAP and Planck have mapped these fluctuations in exquisite detail. The pattern of these fluctuations is predicted by inflation theory. Different models of inflation make slightly different predictions. By carefully studying the cosmic microwave background, astronomers can test different inflation scenarios. Some models predict particular patterns of polarization in the radiation. Others predict specific relationships between temperature fluctuations at different scales. The data so far broadly supports the general predictions of inflation, though questions remain about which specific inflation model describes our universe. And at the heart of this predictive power lies the Planck scale. The quantum fluctuations at the beginning of inflation had wavelengths on the order of the Planck length. These fluctuations grew to become the density variations we observe in the universe today. Without understanding quantum mechanics at the Planck scale, we couldn't explain the large-scale structure of the universe. You might think that we can't observe Planck-scale physics directly, so how can we know anything about it? But this is where cosmology becomes a tool for studying quantum gravity. The early universe acts as a laboratory for testing Planck-scale physics. By carefully observing the universe today, its large-scale structure, its history, its fundamental constants, we can infer what must have happened at Planck scales. Take a breath. Let's consider what the Planck scale tells us about the universe's beginning. If the Planck length is the smallest meaningful distance, then distances smaller than this don't exist in any meaningful sense. This suggests that the universe cannot have been arbitrarily concentrated at the Big Bang. There's a natural lower limit to how small a region the universe could have been compressed into, roughly 1 Planck volume. But wait, if the universe fit into 1 Planck volume at the Big Bang and it's now billions of light years across, then it has grown by a factor of roughly 10 to the 90. That's a growth of 90 orders of magnitude, and the universe is still expanding. This enormous growth over 13.8 billion years requires either an incredibly long period of slow expansion or a much shorter period of exponential expansion, or both. Inflation provides the exponential expansion. The slow expansion we observe today provides the fine-tuning. This raises a profound question. Why did inflation stop? If exponential expansion is so favorable, if it solves so many cosmological puzzles, why didn't the universe remain in an inflationary state forever? In inflation theory, inflation ends because the inflaton field, the field that drives inflation, decays into ordinary particles. This decay releases the energy that powers inflation, which is converted into the hot, dense plasma of particles that makes up the early universe after inflation ends. But the transition from inflation to ordinary expansion is itself mysterious. It depends on quantum fields and their properties. It depends on the potential energy landscape of these fields. And at the Planck scale, quantum fluctuations in these fields become significant. The transition might be probabilistic, a quantum tunneling event where the inflaton field transitions from an inflating state to a non-inflating state. Different regions of space might tunnel at different times, leading to a universe with many different regions, each with different physics. This is related to the idea of the multiverse, the possibility that our Big Bang is just one event among many in a vast landscape of universes. Here's something beautiful to gently contemplate. If these theories are correct, then the universe we observe, with its galaxies, stars, planets, and life, arose from quantum fluctuations at the Planck scale. The structure we see in the universe ultimately traces back to quantum uncertainty at the smallest possible scales. The universe, in a sense, is written in the quantum foam. Moreover, the fact that the universe exists at all, the fact that it has the properties it does, the fact that stars and galaxies and life emerged, all of this might be dependent on physics at the Planck scale. If the Planck scale physics were slightly different, the universe would be radically different. Maybe no inflation would occur. Maybe the particle-antiparticle asymmetry would be different. Maybe the forces of nature would have different strengths. Maybe the universe wouldn't allow for stars, galaxies, and life. This connects to what's called the anthropic principle, the observation that we shouldn't be surprised to find ourselves in a universe that permits the existence of observers. After all, we exist. So the universe must have properties compatible with our existence. But this raises questions. Is our universe just one of many? Do other universes exist with different physics? Are we just observing a lucky region of a vast multiverse where the conditions happen to allow life? These questions push the boundaries of what science can address. They're deeply philosophical as well as physical. But they all center on the Planck scale, on understanding what happened in the universe's earliest moments and how quantum gravity shaped its evolution. The study of the early universe through the lens of Planck scale physics has revealed something remarkable. The universe is not arbitrary. It has structure. It evolved according to physical laws. And those laws, we're discovering, have roots extending back to the Planck scale. Every star and galaxy, every atom and molecule, every thought and feeling, all of it traces back, through billions of years of cosmic history, to the quantum foam of the Planck epoch. And yet, for all that we've learned, the Planck epoch itself remains mysterious. We can infer its properties through the imprints it left on the universe, but we cannot directly observe it. It remains beyond our current reach, hidden behind the veil of quantum gravity. It's the ultimate frontier of physics, waiting for the next breakthrough in our understanding. The Planck scale calls to us across time, inviting deeper comprehension of nature's deepest secrets. Now, let's gently explore how physicists are attempting to find evidence of Planck scale physics in the universe today. Despite the Planck scale being impossibly small, nature might have left clues, subtle signatures that we can detect through careful observation. The challenge is profound. The Planck length is so incredibly tiny that directly observing it seems impossible. We would need a microscope with a magnification factor of roughly 1 billion to resolve structures at the Planck scale. Or we would need to create particles with energies 1 billion times higher than anything we can currently produce. Yet physicists have developed clever indirect methods to search for effects of Planck scale physics. One approach involves studying the behavior of photons, particles of light, over cosmic distances. If space-time is grainy at the Planck scale, then light traveling across vast distances might be affected. The graininess could cause subtle distortions or delays in the light's arrival. Different frequencies of light might be affected differently, with higher frequency light experiencing more distortion than lower frequency light. Think of it this way. Imagine looking at a distant object through a frosted glass window. The roughness of the glass causes the image to blur and distort. Similarly, if space-time has a grainy structure at Planck scales, light traveling through space-time would be distorted as it passes through this quantum roughness. Astronomers have searched for such effects using gamma-ray bursts, extraordinarily energetic explosions that release tremendous amounts of high-energy radiation. When a gamma-ray burst occurs in a distant galaxy, its light travels billions of light-years to reach us. Over such enormous distances, any Planck scale effects would accumulate and become more noticeable. Satellites and ground-based telescopes observe these bursts, carefully measuring the arrival times and spectra of photons at different energies. So far, observations haven't definitively detected Planck scale foaming of spacetime, but the searchers have placed constraints. We now know that if such effects exist, they must be smaller than certain limits. This might sound like a negative result, but it's actually valuable. It narrows the possibilities for what Planck scale physics might look like. Another approach involves studying gravitational waves, ripples in spacetime itself, that were first directly detected in 2015 when the Laser Interferometer Gravitational Wave Observatory, LIGO, observed waves from two colliding black holes. Gravitational waves travel at the speed of light and carry information about violent events in the universe, like merging black holes or neutron stars. Gravitational waves offer a unique window into Planck scale physics. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening material, gravitational waves pass through the universe essentially unimpeded. They carry pristine information from their source. If spacetime has quantum fluctuations at the Planck scale, these might subtly affect the propagation of gravitational waves. Researchers have proposed that quantum gravity effects might cause subtle delays or dispersions in gravitational wave signals. Waves of different frequencies might travel at slightly different speeds through the quantum foam, or the quantum geometry of spacetime might cause the waves to scatter slightly. Detectors like LIGO and planned detectors like the Laser Interferometer Space Antenna, LISA, are becoming sensitive enough that they might eventually detect such effects. Take a breath. Let's consider another avenue, the cosmic microwave background. As we discussed, this ancient radiation carries imprints of the early universe. If Planck-scale physics was important in the very early universe, it might have left signatures in the pattern of temperature fluctuations we observe today. Inflation theory predicts specific patterns of temperature fluctuations and polarization. Different models of inflation make subtly different predictions. Some models are inspired by string theory, others by loop quantum gravity, still others by other approaches to quantum gravity. By carefully analyzing the cosmic microwave background data, cosmologists can test which models best fit observations. The Planck satellite, which operated from 2009 to 2013 and was named after Max Planck, mapped the cosmic microwave background with unprecedented precision. Its observations strongly support the inflationary model of the early universe, but the data also constrain the properties of inflation. Certain inflation models are ruled out by the observations, others are favored. This allows physicists to narrow down which approaches to quantum gravity might be correct. Another clue comes from the fine structure constant and other fundamental constants of nature. These constants, numbers like the ratio of the electron's charge to its mass, appear to be precisely tuned. Small changes in these values would dramatically alter the universe's properties. Some values would prevent star formation, others would prevent chemistry, others would prevent atoms from being stable. Why do these constants have their particular values? In some approaches to quantum gravity, like string theory, the fundamental constants are determined by the geometry of extra dimensions. Different configurations of extra dimensions lead to different values of the fundamental constants. If we could determine what values the constants have, we might be able to infer the structure of extra dimensions at the Planck scale. Measurements of fundamental constants have been refined over the decades. Scientists use various methods to determine these values with increasing precision. Some physicists have wondered whether fundamental constants might actually be slowly changing over cosmic time. If they are, this would suggest underlying quantum gravity effects. So far, observations haven't found evidence that constants are changing, but the search continues. Let's pause and consider what observations from gravitational wave detectors might reveal. When two black holes collide and merge, they release tremendous energy in the form of gravitational waves. These waves carry information about the properties of the black holes, their masses, spins, and orbital characteristics. But if quantum gravity effects modify how spacetime curves near black holes, this might leave subtle signatures in the gravitational wave signals. Specifically, physicists have proposed that if spacetime is quantized at the Planck scale, the internal structure of black holes might be different from what general relativity predicts. The singularity at the center might not exist. Instead, there might be a bounce or a transition to some other form of matter or geometry. When two black holes merge, this quantum structure might manifest in ways that affect the gravitational waves emitted. Current gravitational wave detectors aren't yet sensitive enough to resolve these subtle effects. But future detectors, with improved sensitivity, might be able to detect signatures of Planck-scale physics in gravitational wave signals. This would represent a breakthrough comparable to directly observing atoms, finally seeing evidence of the deepest structure of spacetime. Another promising avenue involves studying the behavior of matter under extreme conditions. Neutron stars are among the densest objects in the universe, containing a mass greater than the Sun, compressed into a sphere only about 20 kilometers across. The density inside a neutron star approaches the Planck density in localized regions. The matter there exists under conditions so extreme that quantum effects become important. By studying neutron stars through observation and theoretical modeling, physicists can learn about matter under extreme conditions. Observations of neutron star properties, their masses, radii, cooling rates, constrain our theories of matter and help us understand physics under extreme conditions. Some researchers speculate that at densities approaching the Planck density, exotic phases of matter might exist that we've never encountered before. You might think that astronomy is our only window into Planck-scale physics. But actually, particle physics experiments on Earth offer another perspective. While we cannot directly create particles with Planck-scale energies, we can study what happens when particles with the highest available energies collide. The Large Hadron Collider at CERN accelerates protons to energies of a few trillion electron volts, making them collide head-on. At these collision energies, physicists search for evidence of extra dimensions, supersymmetry, and other predictions of quantum gravity theories. So far, no signs of extra dimensions or supersymmetry have been definitively detected, but this has led to important constraints. We now know that if supersymmetry exists, the superpartners must be heavier than certain values. If extra dimensions exist, they must have sizes smaller than certain limits. These null results are not failures, they're actually quite valuable. They narrow the parameter space for viable theories of quantum gravity. They tell us what we won't find, which is just as informative as what we do find. Some physicists have proposed even more creative methods to search for Planck-scale physics. For instance, if the universe went through an inflationary phase driven by quantum gravity effects, the gravitational waves produced during inflation might still be traveling through space today. These primordial gravitational waves would have characteristics that depend on the properties of inflation, which in turn depend on Planck-scale physics. Current gravitational wave detectors aren't sensitive enough to detect primordial gravitational waves, but future space-based detectors might be. If detected, primordial gravitational waves would provide direct evidence about the inflationary era and, by extension, about Planck-scale physics in the early universe. Another fascinating possibility involves quantum entanglement. Some physicists have proposed that spacetime itself might be woven from quantum entanglement at the Planck scale. In this view, two regions of space are connected, entangled, at the deepest level. The large-scale smoothness of spacetime emerges from the structure of this quantum entanglement network. If true, this would suggest that information theory and quantum mechanics are more fundamental than spacetime itself. Testing such ideas is extraordinarily challenging. It requires developing new theoretical frameworks and new ways of thinking about spacetime. But if correct, it would represent a profound shift in our understanding of reality. Spacetime wouldn't be fundamental, information and entanglement would be. Here's something to gently ponder. We are living in an era of extraordinary opportunity for discovering Planck-scale physics. Gravitational wave detectors are becoming more sensitive. Space-based observatories are scanning the universe with unprecedented precision. Next-generation particle accelerators are being planned. Theoretical physicists are developing new frameworks and making new predictions. All of these advances are converging toward a goal: understanding what happens at the Planck scale. Not just are we approaching better observational windows into Planck-scale physics, we're also developing new mathematical tools and theoretical frameworks. Researchers are making connections between quantum information, quantum entanglement, thermodynamics, and geometry. These connections suggest that a deeper understanding is possible, that we can weave together seemingly disparate areas of physics into a unified framework. Some physicists propose that the next major revolution in physics will come from understanding how spacetime emerges from more fundamental quantum structures. Just as thermodynamics emerged from statistical mechanics and chemistry emerged from quantum mechanics, perhaps spacetime will be understood as emerging from quantum information theory or from some other deeply fundamental layer of reality. This emergence of spacetime might explain several mysteries simultaneously. It might explain the origin of the Big Bang. It might explain why gravity is so much weaker than other forces. It might explain the values of fundamental constants. It might provide a unified framework encompassing string theory, loop quantum gravity, and other approaches to quantum gravity. we cannot yet be certain that we're on the right track. The universe might surprise us. Nature might operate according to principles we haven't yet imagined. The Planck scale might hold secrets that current theories completely miss. But the very fact that we can ask these questions, that we can design experiments and observations to test our theories, that we're making progress in understanding the deepest layers of reality, this is cause for wonder. The search for Planck scale signatures is not merely an academic exercise. It's humanity's attempt to understand the nature of reality at its most fundamental level. It's an expression of curiosity, of the desire to know, and slowly, patiently, through careful observation and theoretical reasoning, we're beginning to unveil the mysteries hidden at the Planck scale. We're learning that nature is far richer and stranger than our everyday experience suggests. And we're discovering that the smallest scales hold the key to understanding the largest, that the universe's greatest secrets are encoded in its tiniest structures. Let's settle in and explore the profound uncertainties that remain. Despite all our theoretical frameworks and observational efforts, the Planck scale continues to hold mysteries that challenge and perplex even the brightest minds in physics. One of the deepest mysteries is this: what is time really? We've discussed how time might be quantized, how it might emerge from quantum geometry, how it might lose meaning at the Planck scale. But we still don't have a complete understanding. Is time fundamental, or is it emergent? Does time flow, or is that merely an illusion created by our consciousness? Does time have a direction, or is the arrow of time merely a statistical effect? These questions sound philosophical, but they have profound physical implications. Different approaches to quantum gravity handle time differently. In string theory, time is treated somewhat like a fundamental parameter, though it gets woven into the quantum geometry of spacetime. In loop quantum gravity, time emerges from relationships between quantum geometric degrees of freedom. In causal dynamical triangulation, spacetime is fundamentally four-dimensional, but the notion of a preferred time direction emerges only at larger scales. None of these approaches fully resolves the deep puzzles about time's nature. We might need an entirely new conceptual framework to truly understand time at the Planck scale. Perhaps time is not the right category to use at all. Perhaps we need to think in terms of quantum information flow, or quantum entanglement, or some other structure we haven't yet conceived of. Take a breath. Another profound mystery concerns the nature of information and entropy. We know that black holes have entropy proportional to their surface area, measured in Planck units. We know that this entropy seems to be related to information. But what exactly is this information? How is it encoded? Can information truly be destroyed, or is it always preserved in some form? The black hole information paradox remains unresolved. While many physicists believe the information must be preserved, that it escapes in subtle correlations in Hawking radiation, no one has fully demonstrated how this works mathematically. The challenge is that the Hawking radiation appears to be thermal, completely random. How can such apparently random radiation encode detailed information about everything that fell into the black hole? Some physicists propose that the information might be stored in correlations between Hawking radiation from different black holes. Others suggest that the information might be encoded in the black hole's interior in ways we don't yet understand. Still others propose that quantum gravity effects might modify the evaporation process in ways that preserve information more obviously. But none of these ideas has been fully worked out. The paradox remains. Related to this is another deep question. What is the relationship between space-time and information? The holographic principle suggests that a three-dimensional volume of space might be completely described by information encoded on its two-dimensional boundary. If true, this would mean space itself is emergent, a kind of illusion arising from a two-dimensional information structure. But how exactly does this work? How does three-dimensional space emerge from two-dimensional information? What principles govern this emergence? Here's something to gently ponder. If space-time is emergent, if it arises from something more fundamental like quantum information or quantum entanglement, Then what does this mean for our understanding of causality? In spacetime, causes precede effects. But if spacetime emerges from something atemporal, something that doesn't inherently have a direction of time, how does causality emerge? How does the arrow of time arise from something timeless? These questions push at the very boundaries of what we can conceptualize. They suggest that our most basic intuitions about reality, that space is a container, that time flows, that causality is fundamental, might be approximations or emergent properties rather than fundamental truths. Another mystery concerns what lies beneath quantum mechanics itself. Quantum mechanics describes how systems evolve according to the Schrödinger equation, with probabilities specified by wave functions. But what determines which outcome actually occurs when a measurement is made? This is the measurement problem, one of the oldest puzzles in quantum mechanics. Different interpretations of quantum mechanics propose different resolutions. The Copenhagen interpretation says that measurement causes wave function collapse, converting possibilities into actualities. But what exactly is measurement? When does it occur? The many worlds interpretation says that all possibilities are realized in different branches of reality. But this seems to multiply entities unnecessarily. The pilot wave interpretation proposes that particles have definite positions guided by a quantum field. But this sacrifices the usual relativistic covariance of quantum mechanics. At the Planck scale, the measurement problem becomes even more acute. If we're trying to measure the geometry of spacetime itself at Planck scales, we face the problem that spacetime is what provides the background for measurement. How can we measure the background itself? What does it even mean to measure spacetime? These questions suggest that the measurement problem might be intimately connected to understanding quantum gravity. You might think that understanding quantum mechanics at the Planck scale would resolve these puzzles. But perhaps the opposite is true. Perhaps we need to go even deeper, finding a theory that encompasses both quantum mechanics and gravity, and that reveals what underlies quantum mechanics itself. Let's pause and consider another deep mystery, the hierarchy problem, which we've mentioned several times. Why is gravity so much weaker than the other forces? The Planck mass, the scale at which gravity becomes as strong as other forces, is roughly 10 to the 19 times heavier than a proton. This enormous gap between the Planck scale and the scales we can observe is remarkable and puzzling. Some physicists propose that extra dimensions might hold the answer. If gravity leaks into extra dimensions, it would appear weaker in our three-dimensional world. Other physicists propose new particles or new interactions at intermediate scales that we haven't yet discovered. Still others wonder if the hierarchy might not be a problem at all, if it's simply a feature of our universe that we're asked to accept. The hierarchy problem is important because it might guide us toward new physics. If there's new physics at intermediate scales between the weak force scale and the Planck scale, then the Large Hadron Collider, or future colliders, might discover it. This would provide direct evidence of quantum gravity effects or new fundamental particles. Finding such evidence would be revolutionary. But the lack of evidence so far has led some physicists to propose that perhaps no new physics exists at intermediate scales. Perhaps the hierarchy is a real feature of nature that requires no explanation. Or perhaps the new physics is hidden in ways we haven't thought to look for. Related to the hierarchy problem is another mystery. Why do the fundamental constants have the values they do? The fine structure constant, which determines the strength of electromagnetism, is approximately 1/137. Why this number? Why not 1/100 or 1/200? The electron-to-proton mass ratio is about 1/1836. Why this particular value? No one knows. In some approaches to quantum gravity, like string theory, the values of fundamental constants are determined by the geometry of extra dimensions or other aspects of the theory's structure. In principle, if you knew the exact configuration of these hidden structures, you could predict the values of fundamental constants. But there are so many possible configurations, potentially 10 to the 500 different ones in string theory's landscape, that pinning down the exact configuration seems nearly impossible. This connects to the multiverse hypothesis. If many different configurations are possible, and each leads to different physics, then perhaps all of them are realized in different universes. Our universe would be just one among countless others, each with its own laws of physics. We observe the universe we do because we happen to be observers in a universe whose physics allows for our existence. This is the anthropic explanation. We're not surprised to find ourselves in a universe compatible with our existence. But this raises uncomfortable questions. How scientific is a theory that predicts a multiverse we can never observe? How can we test such a theory? Some physicists embrace the multiverse as a logical consequence of our best theories. Others remain skeptical, arguing that if a theory predicts billions of unobservable universes, perhaps the theory is wrong. Here's another profound mystery. What about the initial conditions of the universe? Why did the Big Bang occur? Why did the universe start in a state of such low entropy? Or did it? In some approaches to quantum gravity, entropy might not have been low at the Big Bang. The universe might have had maximum entropy initially, with entropy remaining constant as the universe evolved. Our perception that entropy is increasing might be a quirk of our local situation, not a universal principle. The second law of thermodynamics, the law that entropy always increases, is so fundamental to our understanding of physics that questioning it seems almost heretical. But at the Planck scale, with quantum gravity effects dominant, might entropy behave differently? Might time's arrow emerge from the evolution of entropy? These questions remain open. Take a breath. Let's consider one more profound mystery: consciousness and the Planck scale. This might seem like an odd connection, but some physicists and philosophers have speculated about whether quantum effects at the Planck scale might play a role in consciousness. Some propose that the brain might be sufficiently sensitive to quantum effects that quantum gravity phenomena could influence neural processes. Others suggest consciousness itself might be a quantum phenomenon, with wave function collapse playing a role in conscious experience. Still others propose that information encoded at the Planck scale might be relevant to consciousness through the holographic principle. These ideas remain highly speculative. Most neuroscientists believe that consciousness arises from classical neural processes in the brain without requiring quantum effects. But the door isn't entirely closed. The brain is, after all, a physical system, and if our understanding of physics is incomplete, if we're missing something crucial about quantum mechanics or quantum gravity, then perhaps consciousness might be relevant to this missing physics. Not just is consciousness mysterious in its connection to physics. Consciousness is itself a gateway to the Planck scale in another way. Our observations of the universe, our measurement of physical quantities, our tests of physical theories, all of these ultimately rely on conscious observers recording and interpreting data. The measurement problem in quantum mechanics centers on this: the role of observation and, by extension, consciousness in physics. If spacetime is emergent, arising from quantum information, then perhaps consciousness, which is related to information processing, plays a deeper role in physics than we usually imagine. Perhaps observation doesn't just reveal pre-existing properties, but actually participates in creating reality at the quantum level. Perhaps consciousness and physical reality are more intimately connected than our usual frameworks suggest. These are speculative ideas, and they challenge many of our assumptions about the relationship between observer and observed. But they point to deep puzzles that remain unresolved. Here's something beautiful to gently contemplate. All these mysteries about time, information, the hierarchy problem, the initial conditions of the universe, consciousness, all of them point toward the Planck scale. All of them suggest that we're missing something fundamental about how reality works, and that missing piece might involve understanding physics at the Planck scale. We stand at a frontier of knowledge. We've developed several promising theoretical frameworks for quantum gravity. We've made observations that constrain these frameworks. We've identified key mysteries that need to be resolved. But we haven't yet achieved a breakthrough, a unified, fully consistent theory of quantum gravity that explains everything and makes testable predictions that distinguish it from other approaches. That breakthrough might come from an unexpected direction. It might come from a brilliant new insight, a clever mathematical technique, or a surprising experimental observation. It might come from a young physicist working outside the mainstream, or from a collaboration of many researchers building on decades of accumulated knowledge. It might come soon, or it might take decades or centuries. But we know it will come. Human curiosity is relentless. Our drive to understand reality is powerful. The Planck scale calls to us, whispering its secrets. And we, in our infinite yearning to comprehend the nature of existence, will continue to probe, to question, to search for answers. We will push against the boundaries of the unknown. And eventually, gently and persistently, we will begin to unveil what lies hidden at the universe's smallest scales. The mystery is profound, but it is not infinite. The Planck scale is not beyond our reach. It's merely waiting for us to grow wise enough, creative enough, and persistent enough to understand it. And when we do, the implications will reshape everything we thought we knew about reality. Now we arrive at the final synthesis, where we gently gather together all the threads of our journey and reflect on what the Planck scale reveals about the nature of wonder, mystery, and human understanding itself. Throughout this long exploration, we've journeyed from the comfortable, familiar world of everyday experience down through layer after layer of reality. We've descended from mountains and oceans, to atoms, to subatomic particles, to quantum fields, to spacetime itself. And at the deepest level we can contemplate, we've found the Planck scale, a frontier where our understanding breaks down and something new awaits discovery. What have we learned? We've learned that space and time are not infinitely divisible. They have a fundamental grain at the Planck scale. We've learned that gravity and quantum mechanics, which seem so different at everyday scales, must ultimately be reconciled at the Planck scale. We've learned that spacetime itself might be emergent, arising from more fundamental structures, quantum geometry, vibrating strings, loops of quantum information, or something we haven't yet imagined. But perhaps more importantly, we've learned that there is much we don't know. We've encountered mysteries that remain unsolved despite decades or centuries of investigation. We've found that our most basic intuitions about reality, that space is a container, that time flows, that causality is fundamental, might be approximations or emergent properties. We've discovered that the universe is far more subtle, complex, and strange than everyday experience suggests. Let's pause and reflect on what this means. We live in a universe where the deepest truths are hidden from direct observation. The Planck scale is so small that we can never directly see it with any conceivable technology. The energies required to probe it directly are so enormous that we can never create them in laboratories. The Planck epoch of the universe is so far in the past that we can never travel there. In some very real sense, the Planck scale is beyond our reach, and yet we can still learn about it. We can infer its properties through mathematical reasoning. We can search for indirect signatures in observations. We can develop theories and test their predictions. We can push against the boundaries of the unknown and gradually expand our understanding. This is one of humanity's greatest achievements, the ability to comprehend what we cannot directly perceive, to grasp the nature of reality through the power of reason and imagination. You might think this is a source of frustration or despair. We can never fully know what happens at the Planck scale. We can never be certain of our theories about quantum gravity. We can never directly verify our speculations about extra dimensions or quantum foam or the holographic principle. There will always be uncertainty, always be mysteries, always be gaps in our understanding. But actually, this uncertainty is a gift. It's what keeps physics alive and vibrant. It's what drives new research, new theories, new observations. If we knew everything, if all the mysteries were solved, if all the questions had answers, what would be left to explore? What would drive human curiosity forward? The Planck scale represents the frontier of human knowledge. It's the place where we acknowledge the limits of what we currently understand. And in acknowledging these limits, we open ourselves to new possibilities, new ways of thinking, new frameworks for comprehending reality. Take a breath. Let's think about what the Planck scale tells us about the relationship between physics and mathematics. Throughout this exploration, we've seen that mathematical frameworks, general relativity, quantum mechanics, string theory, loop quantum gravity, are at the heart of our understanding. These theories make predictions that we test against observations. When observations agree with predictions, we gain confidence in the theory. When they disagree, we must modify or replace the theory. But at the Planck scale, we face a challenge. The scales are so small and the energy so high that we cannot test theories directly. We must rely more heavily on mathematical reasoning and indirect evidence. This raises a profound question. To what extent does mathematics discover truth about reality versus merely being a useful language we've invented? Some physicists, like Eugene Wigner, have been struck by what they call the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical structures, invented by human minds for their own internal consistency and beauty, turn out to describe the physical universe so accurately? Why should the universe obey equations? Is there something special about mathematics itself? Or is the universe fundamentally mathematical? These questions become even more pressing when we contemplate the Planck scale. At this frontier, we're working almost entirely with mathematics. The gap between our theories and observable reality is so vast that we must reason from first principles, from deep mathematical structures. This might be the highest form of human understanding, not the direct observation of phenomena, but the grasping of mathematical structures that underlie reality. Or perhaps, conversely, it means we've gone too far into abstraction. Perhaps our mathematical frameworks, however elegant, are leading us away from truth rather than toward it. Perhaps we need a different approach, less reliant on mathematics and more grounded in physical intuition and observation. These questions cannot be easily answered. They reflect genuine uncertainties in how we should pursue physics at the frontier of the unknown. Here's something to gently ponder. The Planck scale might represent not just a boundary of the very small, but a boundary of comprehensibility itself. Perhaps there are aspects of the universe that are fundamentally unknowable, not because we lack sufficient intelligence or technology, but because they exist beyond the realm of what can be known. Perhaps consciousness itself is limited in ways we don't yet understand, ways that prevent us from fully grasping certain truths about reality. Some physicists and philosophers have proposed that there might be limits to human understanding, not merely practical limits. We can't build accelerators large enough, but fundamental limits rooted in the structure of knowledge itself. If consciousness arises from physical processes, and those physical processes operate under quantum mechanical rules, then perhaps there are intrinsic limits to what any conscious being can know about reality. Yet this too is speculative. We cannot be certain that such limits exist, and even if they do, they shouldn't stop us from trying. The very attempt to understand, to push at the boundaries of knowledge, to explore the frontier of the unknown, this itself has value. It's part of what makes us human. Not just does the Planck scale represent a boundary of small size, it also represents a boundary in time. The Planck time is the smallest meaningful interval of time. Earlier than one Planck time after the Big Bang, our theories of physics break down. We cannot predict what happened before that moment. We cannot even ask coherently what before means in that context. This raises a metaphysical question. Does time have a beginning? If the Big Bang represents a true beginning of time, then asking what came before is meaningless. But if the Big Bang is not a true beginning, if it's a transition or a bounce or a collision in a higher dimensional space, then time might extend infinitely into the past. Different approaches to quantum gravity suggest different answers. What's remarkable is that this question, so ancient, so philosophical, so removed from everyday physics, is now being addressed by quantum gravity research. Modern physics has reached a point where it's probing the very metaphysical questions that philosophers have grappled with for millennia, and it's doing so through mathematics and observation, through the rigorous methods of science. This suggests that the boundary between physics and philosophy is not as clear as we, sometimes, imagine. At the frontier of our understanding, at the Planck scale and beyond, physics and philosophy inevitably intersect. Questions about the nature of reality, the nature of time, the nature of existence itself, these are both physical and philosophical questions. Let's pause and consider what all of this means for how we see ourselves in the universe. We are conscious beings arising from matter, from atoms and molecules arranged in extraordinarily complex configurations. Those atoms are made of subatomic particles. Those particles are excitations of quantum fields. Those fields exist in spacetime. And spacetime itself might emerge from quantum geometry or quantum information at the Planck scale. In other words, you and I, our thoughts, our feelings, our experiences, ultimately arise from the quantum foam at the Planck scale. We are, in the deepest sense, made of Planck scale physics. The structure we see in ourselves and in the universe traces back through billions of years of evolution to the quantum fluctuations of the early universe, which themselves trace back to the Planck epoch. We are made of stardust, but that stardust is ultimately made of quantum geometry at the smallest scales. This might sound like we're insignificant, that we're just tiny expressions of vast physical forces operating at scales far beyond our perception, but actually, it can inspire a sense of profound connection and wonder. We are not separate from the universe. We are the universe experiencing itself, contemplating itself, trying to understand itself. The atoms that make up our brains were created in the cores of stars that exploded billions of years ago. The carbon in our bodies was forged in those stellar furnaces. And the laws that govern our carbon atoms are laws rooted in the Planck scale, in the deepest structure of space-time. You might think that understanding the Planck scale would make the universe less mysterious, less wonderful. But the opposite seems to be true. The deeper we look, the more we discover how strange and beautiful reality truly is. The more we understand about quantum mechanics and gravity, the more we realize how little we know. The universe reveals itself to be far richer, far more intricate, and far more surprising than we ever imagined. Here's something beautiful to gently contemplate. We live in an age of unprecedented opportunity for understanding the Planck scale. Our telescopes are becoming more powerful. Our gravitational wave detectors are becoming more sensitive. Our particle accelerators are reaching higher energies. Our theoretical frameworks are becoming more sophisticated. Our mathematical tools are advancing. And human creativity, that remarkable ability to imagine new possibilities, to make intuitive leaps, to see patterns and connections, continues to flourish. The breakthrough might come soon, or it might take decades or centuries, but it will come. The mysteries of the Planck scale will eventually yield to human inquiry. And when they do, the understanding that emerges will reshape our comprehension of reality as profoundly as Newton's theories reshaped understanding in the 17th century, or Einstein's theories in the 20th century. But even after that breakthrough, new mysteries will emerge. For every question we answer, new questions arise. The universe seems to have infinite depths of complexity and strangeness waiting to be discovered. The Planck scale is not the ultimate frontier. Behind it, beyond it, there might be even deeper structures, even more fundamental layers of reality that we can barely imagine. This is the essence of scientific pursuit, the recognition that understanding is not a destination, but a journey. We never reach a final answer that explains everything. Instead, we progress gradually, solving old mysteries and discovering new ones. Each answer opens new questions. Each theory, no matter how successful, eventually shows cracks that hint at something deeper beyond. And this is not a source of despair, it's a source of wonder. It's an invitation to keep exploring, keep questioning, keep searching. The universe is inexhaustible. Reality is deeper than any finite understanding can reach. And that's beautiful. Not just is the Planck scale important for physicists and cosmologists, it's important for all of us who wonder about the nature of reality. It reminds us that the universe operates according to laws. It shows us that these laws have deep mathematical structure. It demonstrates that human minds, products of evolution, neurons firing according to electrochemical processes, can grasp truths about the nature of reality itself. It inspires awe at the sophistication and intricacy of the cosmos. The Planck scale is where physics touches metaphysics, where measurement confronts mystery, where human understanding reaches toward infinity. It's a threshold, not a barrier, but an invitation. It calls to us to grow, to learn, to expand our comprehension. It whispers that there are deeper truths waiting to be discovered, structures more beautiful than we've yet imagined, mysteries more profound than our current theories can address. And so our journey concludes, or rather, it doesn't conclude. It merely pauses for a moment of reflection before continuing onward. The Planck scale waits, patient and mysterious, for the next generation of physicists and theorists and dreamers to push at its boundaries, to probe its secrets, to gradually unveil what lies hidden at the universe's deepest level. As we prepare to close this exploration, let's carry with us a sense of wonder. Wonder at the vastness of space and the billions of years of cosmic history. Wonder at the intricacy of atoms and the complexity of life. Wonder at the beauty of mathematical structures that describe reality. And most of all, wonder at the fact that we can wonder at all. That consciousness itself has emerged from the universe, that we can contemplate and understand aspects of reality, that we can reach toward truth even when it hides beyond our perception. The Planck scale is not an ending. It's a beginning, the beginning of a new frontier, the threshold of deeper understanding. And humanity, with all our curiosity and creativity and determination, continues to move toward that threshold, gently and persistently, one discovery at a time. Is there a smallest scale in space and time? It's the question that brought us here, whispered softly at the beginning, like a child asking if the ocean has a bottom, if stars have hearts, if the universe itself might have edges and boundaries we could someday reach. And after wandering through the landscape of quantum gravity, string theory, loop quantum geometry, black hole thermodynamics, and the mysteries of the early cosmos, we find ourselves gently circling back to where we began, still wondering, still in awe. We've learned so much together during this long, peaceful journey. We've discovered that space and time are not infinitely divisible. The Planck length, that incomprehensibly small distance of roughly 10 to the negative 35 meters, represents a fundamental boundary beyond which our current understanding falters. We've explored the Planck time, that briefest of moments lasting 10 to the negative 44 seconds, which might represent the smallest meaningful interval in the universe. We've contemplated quantum foam, that seething substrate of virtual particles and quantum fluctuations churning at the very foundation of spacetime. We've journeyed through the elegant mathematics of string theory with its extra dimensions curled up at Planck scales, and we've drifted through the geometric beauty of loop quantum gravity, where spacetime is woven from discrete loops of quantum geometry. We've examined how black holes connect intimately to Planck scale physics, how their event horizons might be made of Planck area units, how the information paradox hints at deep truths about the nature of spacetime and information. We've traced the universe's history from the mysterious Planck epoch through cosmic inflation to the vast cosmic structure we observe today, all emerging ultimately from quantum fluctuations at the smallest scales. We've searched for signatures of Planck scale physics in gravitational waves, cosmic radiation, and the fundamental constants of nature. And we've encountered profound mysteries, questions about time's nature, about consciousness and reality. about what lies beneath quantum mechanics itself, that remain beautifully, tantalizingly, unresolved. Maybe the Planck scale doesn't have a simple explanation. Maybe there's no single unified theory that will resolve all mysteries and answer all questions. Maybe the universe is fundamentally more complex, more subtle, more infinite in its depths than any finite theory can capture. Maybe that's precisely the point, that reality remains forever mysterious, forever inviting deeper inquiry, forever calling us to expand our understanding. The Planck scale might not be a destination but a horizon, always receding as we approach it, always suggesting new frontiers beyond. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned several things about the Planck scale, quantum gravity, and the deepest structure of spacetime along the way. And if you're already drifting towards sleep, or if you've just arrived in that peaceful place between waking and dreaming, where thoughts drift like clouds across a gentle sky, may your sleep be deep, and may your dreams be filled with softly glowing equations, gently vibrating strings, and peaceful geometric patterns woven from quantum loops. You might find yourself dreaming of the Big Bang, not as a violent explosion, but as a soft unfurling, of spacetime, not as a stage, but as something alive with possibility, of the universe not as a mechanism, but as a meditation on existence itself. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world right now. Drop a comment and share. Are you perhaps a physics student pondering these profound mysteries of quantum gravity, or someone simply fascinated by the cosmos and how it works? Are you listening from a quiet bedroom late at night, or from a comfortable study while the afternoon light gently fades outside your window? Are you a researcher working on quantum gravity theories, or simply a curious mind wanting to understand the nature of reality? It's always such a joy to hear where you are and what brought you to this exploration of the Planck scale. If you found this gentle journey into the Planck scale, quantum gravity, and the deepest mysteries of space-time relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content about physics, cosmology, and the wonders of the universe. Each subscription, each like, each kind comment encourages me to continue creating these long-form explorations of science's greatest mysteries. Your support means more than you might imagine. Thank you for joining me on this journey through the Planck scale, through quantum gravity and the fundamental structure of reality. Thank you for your curiosity, your patience, and your willingness to contemplate mysteries that physicists have grappled with for decades. Sleep well, dream deep, and may your thoughts rest gently in a universe made of quantum loops and geometric beauty at its deepest level. Remember that somewhere in the quantum foam at the Planck scale, infinite versions of you are already peacefully asleep, their dreams woven from the same cosmic fabric as ours. And that's rather wonderful when you think about it. Good night.